Good evening.
Good evening, everybody.
Yes.
Woohoo!
Takeover After Dark. Oh, darn it.
Welcome back to Takeover After Dark, summer school. Are you guys ready for this? All right, this is going to be fun. We're back. We have a nice little 2-week hiatus, and it's good to be back. We were just discussing off air here about what did we do the last 2 weeks? I mean, Wednesday night rolled around the last 2 weeks, and all three of us were kind of moping around the house looking for something to do, you know, except Rick. He was moping around the house in the middle of the afternoon, but the rest of us were moping around the house at night, wondering where all our friends were and what were we going to do, man. I watched a lot of 2.5 Men reruns on the last 2 Wednesday nights.
Yeah, I think I was still on the computer anyway, just because I had to be down here.
Yeah, no, that's it. You get, well, I think your wife sends you down there after dinner every night just to
get away.
Yeah, go downstairs and behave yourself, right?
I'm not supposed to be here, yeah.
Yeah, there you go. All righty. Well, welcome everybody. John Barba, Rick Mayo, Dave Holdorf, or Mr. Shoop, as you will. Back and ready for a nice summer session. So this is going to be kind of fun for Takeover After Dark. Tito's and tonic for Jerry McPeak. That's pretty good, man. That's his drink of the evening. What do you have, Dave?
I am mixing myself up a margarita right now.
Oh,
not a
nice.
mayo-rita. I haven't had the chance to go shopping for a mayo-rita, but I'm having a margarita tonight.
All right, and Mr. Mayo, what do you have?
Mayo-rita.
You have a mayo-rita. Well, I have Poland Spring sparkling water, lime infused.
Nice. Extra lime.
Yeah, with extra lime. So I may wind up like belching in the middle of this thing if I'm not careful. So, but hey, that's all right. We're all grown-ups here. So welcome to Takeover After Dark, the summer school edition. And there's our man Bruce Campbell, the unofficial mascot of Takeover After Dark. And you know, before with Takeover After Dark, he was previously he was in the library in his nice leather chair at the Ascot in the smoking jacket. Well, it's summer school, right? So he's in the hot tub with a mojito. All right, that's where we're at. This is going to be a little bit different. All right, it's going to be a little bit different for summer school. I've still got my wardrobe, if you can guess the movie right here. Say what again? So our movie theme tonight is going to be, of course, Pulp Fiction. And the summer session is going to be kind of different. It's going to be informal. We're going to have a nice little informal summertime vibe. So we're going to have some fun, and not like the regular classes were overly formal. We weren't. That's just not us.
Except for me.
We're going to, except for Dave, who had to go out and buy new ascots. Well, he didn't have to go out and buy new ascots. They were a part of his collection. We're going to relax a little bit and enjoy ourselves and do some things a little bit differently this go round. We're still going to have our presentations, but what we're going to do, we're going to do a project this during the summer school. Basically, start with a set of blueprints and go all the way towards building a mechanical room. But included in all this, we're going to crowdsource our next topics. So every week we're going to spend maybe 15-20 minutes working on the project, and then after that we're going to change the topic for something else, and we're going to let you guys decide. So a little bit later on, we're going to run a poll where you will get to choose among the different topics that we have available. You'll get to vote for which one you want. And then we're also going to run the poll on social media as well. And John Messenbrink, you're with us. I mean, if you want to run it on Mechanical Hub, that would be awesome. And we'll crowdsource, and we'll get to do what you guys want. So it could be wiring, it could be boiler water treatment, it could be combustion. It could be whatever you want, whatever gets the most votes. Okay, that's what we're going to do. So I think it's going to be kind of fun and kind of a little bit different. And John, anything you'd like to say to the crowd as we get ready to work our way back into summer school?
Welcome back. 2 weeks off. I felt a little naked and afraid. I think I told you guys earlier, but
thank you for that. I'm not going to get that out of my head now. Okay.
I did have a question. Is that the wolf in that picture?
That is Winston Wolfe. That is Winston Wolfe. He was my second favorite character in that movie, right there, Winston Wolfe. The wolf.
No,
please,
but
pretty please, with sugar on top. Wash the car.
Thank you three. Awesome stuff, and thanks everyone for for spending a little Wednesday nights with us. So it's awesome.
Excellent. As always, we'll stay on as long as you guys want us to stay on to yak and answer whatever questions you might have. We're happy to do it. So real quick, I want to go over some of the control panel stuff. Okay, you should see that little hand on your control panel. There's that arrow. Okay, you see this little arrow up top. Click the arrow, and that'll expand the control panel, so you'll be able to see it. All right, so click on it to expand the control panel. Now, do you see that little thing that looks like a hand? Just press that for me. And that's going to be like raising your hand. That way I know you can hear me, and so far so good. Everybody out there can hear me. Excellent. Terrific, terrific, terrific. So that works. In addition, the expanded control panel is going to allow you to do some things. So specifically, you've got your audio selection up top there, okay? Handouts. We've got several handouts that I'd like you to download, especially right away. There's a handout in the handout section that I want you to download right now. Called the TACO After Dark Heat Loss Info Package. We're going to be using that tonight. You can download all three. We also have the TACO Wholesale Products Catalog, which you're going to love. It's just a catalog of everything we have, as well as the TACO Ways training brochure that has some interesting tables and formulas and stuff in there for us. Please download all of that, but make sure we use the TACO. You keep the TACO After Dark Heat Loss Package handy, because that's what we're going to be using tonight, and basically you're going to have a little project, a little homework to do during the week. So I want you to work on that. So that's all in the handout section. All right, so make sure you guys get a look at that. In addition, you're going to see the section for questions. All right. So it says questions chat on when you expand your control panel. That's just going to be how you're going to type in a question or type in a suggestion or type in a comment. I'd like everybody to do that right now. Again, I got 97 of you out there. If you could just open that thing up and type in hi, hello, how are you? Anything that strikes your fancy, please go ahead and do so. Just so I know that you know how to do this. All right, good. Oh, look at that. It populates like crazy. Excellent. Very good. So everybody knows how to do that. And as we go along, friends, please make sure to just type in, when you have a question, when a question comes to you, please type it in. And we'll be monitoring the questions as we go through, and then we'll take a break every few slides to say, hey, okay, let's go over this question. So keep it kind of interesting, and you're not listening to just one voice drone on and on and on like listening to me. You get to hear the other guys who are, quite frankly, much more interesting than I am. So with that, let us continue. All right, here's your chat section. You just type in a question there. Again, most of you guys have figured that out, which is excellent. And in the spirit of Jules and one of the great movies of the 90s, Pulp Fiction, let's grab ourselves a tasty burger and let's get started. All right. So step one is what we're going to do is we're going to do a heat loss for this house. Okay, this is house in the project that we're working on in that heat loss package. So I want you to make sure you download that. If you have enough room on your screen, or if you have a separate monitor, open it up and take a look at it. But we're going to walk through it. And what we're going to do tonight, it's a whole house heat loss. What we're going to do tonight is we're going to do one room together upstairs, and then we're all going to do the basement together. So you get an idea how basements are done below slab. After that, you guys are going to do, over the course of the next week, leading up to next week, use what you've learned here and just do the heat loss calculations for the entire house. Honestly, it shouldn't take you more than 15, 20 minutes if you dawdle. All right, but I want to make sure everybody knows how to do that and has a little bit of practice using the package. And then from there, we're going to zone this thing out. We're gonna put in different types of radiators. We're going to put in radiant. We're going to put in a boiler. We're going to size circulators and zone valves, indirect, the whole shoot and match. We're going to put the whole thing together as we go through the project over the next several weeks. So again, make sure you download that design heat loss handbook and print it out if possible. If you're sitting right next to your printer, hey, print it out, and then you can be able to look at it. I think it's about 20 pages or something, but you'll be able to look at everything as we go through the program. I'd also like you to have a calculator, a pad, and a pen with you, so you can take notes, obviously, but also do the math along with us as we go. So the first thing we're going to do with our project is we're going to fill out a spec sheet. one of the first pages in there is a specification sheet. It's just a place for us to write down the different factors that we're going to use in the course of our project. So for our project, what we're doing is this house, okay? This house, this is the first floor. All right, it's a main floor and a basement floor. So it's really just one level, but the basement is going to be heated as well. So we see a garage, we see bedroom, 3 bedrooms, family room, kitchen, dining room, living room, entry, a couple of bathrooms, all on the first floor. All right. And then we go down to the basement level, okay, which is 55.5 by 25. And it's one big room at this point. And we're going to try to heat that thing anyway. We want to get a heat load for that thing. Figure it as one big room, and we're going to work with that. But what I would like you to do, and Dave, if you can launch that poll, okay?
It is out there.
It is
It's
out there.
there.
So we have a
Yes.
poll based on what you're seeing here, folks. Okay, based on what you're seeing, with this, basically 2 stories, 25 feet by 55.5 feet. What is your best estimate of a heat loss? All right, what is your best estimate based on years and years and years of your experience? All right, in the industry, what's your best guess? So we're collecting responses here. All right.
Yeah, take a look at, oh, we're going to tell you to do a heat load real fast. We didn't tell you the square footage or anything, but just look at it, see what your gut is, what your experience is, what you've seen out there. So, because we're going to go through the details on that anyway. So, but yes, thank you. I got about 45% of you have voted so far. So,
Alright.
for those of you that haven't, please do. It's a good area for us to take a look at too. I like to see the numbers, and John and I have been doing this class for a bunch of years now, so it's always good to see the numbers and see what people think about stuff.
Yeah, we have 60% of the precincts now reporting. There we go. All right. So we got 112 of you. So let's make sure everybody's voted. We'll give you a couple seconds to take a look. But again, we haven't told you where the house is yet. We haven't told you the type of insulation yet. We're just looking. Everybody looks at us and says, "Yeah, that's going to be about. That's going to be about." I want to see what you guys think it's going to be about. All right. So very good. We got almost 70% of the precincts counted.
All right, sounds good.
All righty. So we'll let that stay open for a few more minutes, and we'll mosey on along here. And what we're going to do is go through this process and do the heat loss calculations. Now, in that package, one of the first things you see is this specification sheet, and it tells you the specifics of the project, like where it is, etc. And then it tells you the type of wall, the type of ceilings, the type of windows, and then asks you to look up in the book what the different U values are for those assemblies, and we'll show you how to use those. Now, all of these charts and graphs come to us by permission from AHRI. AHRI years ago absorbed IBR, all right, the Institute for Boilers and Radiators. It absorbed IBR, and IBR was the way I learned how to do heat loss. It goes back to the long time ago, but I remember going to a three-day class on nothing but heat loss at the Holiday Inn at the Traffic Circle in Portsmouth, New Hampshire, back in 1988, I think, 1989. Learned a ton. Remains one of the best classes I've ever been to. But we're gonna kind of compress all of that into one short program. But all of the charts that we're going to be looking at come from the IBR H-22 Heat Loss Design Guide. The IBR H-22 Heat Loss Design Guide. Now that can be purchased through AHR if you go online, or Amazon. You can probably get it on Amazon as well. They're about $30, and it's a full 110-page, 8.5 by 11 sized book that has all this information in it. But you've got the important stuff in the appendixes are here for you for free. So what we're going to do is we're going to fill out our project specs. So we got our location, Norwich, Connecticut. We need to know our outdoor design temperature and our indoor design temperature. We have to figure out, looking up in the charts, we have to figure out what the U value is for that particular wall assembly. Ceilings, windows, doors, walls, the whole shoot match is going to be figured out. So for our purposes, the first thing we want to do is figure out what's the outdoor design temperature for Norwich, Connecticut. So looking in the appendix in table 1, all right, we have a chart here, and it's several pages long, of outdoor design temperatures for all over the country. Now, right off the bat, it defines what outdoor design temperature is. Outdoor design temperatures, ODT, for representative cities at 97.5% frequency level per AHRI 90A-1980 recommendation. All right. Use different OTD if local conditions indicate the need. Now, the second number on this is always heating degree days below 65. We can show you how to use those in a subsequent program. But what this does, it just shows you the different recommended outdoor design temperatures for different parts of the country. So we've got Alabama, Alaska, Arizona, yada, yada, yada. And now we're going to look at Connecticut. And that AHRI designed recommendation, 97.5 frequency level. That means that 97.5% of the time in a given area, it doesn't get colder than the stated temperature that we're looking at. That means 2.5% of the time it does, but 97.5% of the time it doesn't. The times that it doesn't, that it's going to be, or the times that it does get below that number, statistically speaking, it is actually about 54 hours intermittently over a 54-hour period in January, February of every year. So that they're intermittent early morning hours where they generally see that dive. They actually figured it out. Now, that it's not an absolute. Sometimes you get those crazy cold snaps, but it is what it is. So
Right.
taking a look.
Remember, I mean, this is a bunch of engineers that have recorded this data. No offense to the engineers out there, but they've recorded this data over the last, 80 some odd years. And remember, what's colder than 7 degrees to an engineer? All right. That's what you got to remember right now. What's colder than 7 degrees to an engineer out there? Go ahead, type something in there. I just want to see some of the answers out there.
Yeah, there you go. What is colder than 7 degrees? I know the answer.
Yes, James, he remembers 6.99 degrees is colder. So yes. So even 6 degrees is way too much of a spread to go with there. So as soon as you get to 6.99, whoop, that goes under that 2.5%. So the point is, trust the number. Trust it. Okay. When I used to do designs on Long Island where I am, it's 14 degrees above zero. Nobody believed me. I said, that's the number. That's what it is. So just remember to trust it. Yes.
Yep. Oh, just crack the sparkling water. Hang on a second.
Oh, no worries. So that's the important part, is to trust that number. So
right. So let's take a look at Connecticut and find Norwich, Connecticut. All right, we take a look down here. Norwich, Connecticut, the outdoor design temperature is 7 degrees. So far, so good. So we go to our project specification sheet and we put our outdoor design temperature of 7 degrees, and then we decide what our indoor design temperature, meaning we want to maintain this indoor design temperature at 7 degrees outdoors, and typically we just choose 70. All right, some jurisdictions still require 72. Some radiant companies will say design to 68 or 65 because radiant's just plain different. For our purposes, we're going to choose 70 degrees. So my IDT, indoor design temperature, is 70. My outdoor design temperature is 7. That means something known as the DTD, or design temperature difference, is 63 degrees. 70 degrees indoors minus 7 degrees outdoors. My design temperature difference is 63 degrees. It's the spread between the indoor and the outdoor. That's an important number because we're going to use that later when we start doing our math. So that design temperature difference is the number we're looking for. All righty. Next up, we want to do walls. And according to this, our walls are framed up, wood frame walls with insulation-backed vinyl siding, 5/8-inch plywood sheathing, 2x6 studs on 16-inch centers, R19 insulation with vapor barrier, and a 1/2-inch drywall. Now, how do we figure out the U value for that? Well, again, these charts have everything in there. So we go to the charts. All right, we go to the charts and we find different types of framed walls. Okay, section 11, framed walls with aluminum or vinyl siding. Okay, so we look and see what fits our description here. So we get insulation backed with sheathing. All right, 2x6 studs, 16 inches on center right here, 6 inches of fiberglass, R19, vapor seal, yes, 1/2-inch drywall, and there's our U value, 0.058. Now, U value, again, make sure we understand what a U value is. A U value is a measure of a material's ability to conduct heat. In construction, we want as low of a U value as we can possibly get. The lower the U value, the less capable a structure is of conducting heat from one side to the other. which is perfect because when it's cold outside, we want to keep the heat inside. We don't want to conduct it. We don't want to conduct it from inside to outside. We want to keep it inside. Conversely, in the summertime, when it's hot outside, we want to keep the heat outside. So we want, again, a low conductive value. So this particular example, the number we're going to use is 0.058. All right. So far, so good. So for walls, we'll put in 0.058. Ceilings, now again, when we talked about this the first time, the only time we do a ceiling loss is when there's no heated space above, all right? Whether it's an attic, a built-up roof, something like that, there's no heated space above. For our first floor, clearly there will be no heated space above, so we will have to figure a ceiling loss. Our ceiling construction here is 1/2-inch sheetrock, R44 insulation, no floor above, unheated over the entire area. So it's just a built-up attic. So we got to go look that up. All right. So we'll look up. Whoops, I'm sorry. We will look up our ceilings. Oh, and we went right to windows there. So behind there, there's a. I'm sorry. I'm going to do something really shady here, real quick, because I goofed up. I didn't make that work. So right here, you see, we have our ceiling with attic space above. All right. Ceiling with attic space above. We go to line K, and there it is, 1/2-inch drywall with or without a floor above, R44 insulation. That factor, what we're going to use is 0.02, or 0.02 is our factor for the ceiling. All right, 0.02 is the factor for the ceiling. So let me get the presentation back up here. All righty, there we go. All right, we forgot our animation. All right. And now we want to find our window. All right. Our window was a low E double pane vinyl frame window with a storm sash. Okay. So we take a look at that. There's our low E double pane window. All right. Wood, it was a vinyl frame. I'm sorry, vinyl frame without a storm sash. There was no storm window on this. So if we take a quick look at that, we find that the U value for that window is 0.36 or 0.361. So we have our ceiling U value factor, and now we have our window U value factor, and we can pump those in at 0.02, and for the window, 0.361. So again, I want to check in with you guys and make sure we're all good. Is everybody kind of understanding? Any questions that we have that have come up here? If this is making sense to you, are we jumping around a little bit? Let me know what your thoughts are and how we're doing here as far as filling in the blanks here and getting the information. Just a matter of getting yourself familiar with these charts and looking where to find stuff. Now, how are you going to find some of this stuff if you're out in the field trying to do a heat loss for a house that's already been built? Well, a lot of the stuff you're actually going to have to infer. I mean, the windows, you can look at them and see. All right. Insulation in the wall, unless they give you free rein with a sawzall, you're going to have to make some inferences. All right, how old is the house? What's typical construction for houses in that area? This is where your experience and your knowledge of construction in these different areas are going to come into play. All right.
Hey, John.
So, yes, sir.
James has got a question that's relative. We're talking about U value. And there's always this thing that is associated with that, and he's bringing that exact question up. Is the U factor, he's saying U factor, U value related to the R factor? And that's the question.
Yes, it is. That is a very, very good question. Are U values and R values related? They are kissing cousins, so to speak. They are the inverse of one another. All right, they're flip sides of the same coin. If I know a U value, as we said, is a measure of a material's ability to conduct heat from one end to the other, from one side to the other. R value is the exact opposite. It's a material's ability to resist the flow of heat. So a very low U value will have a very high R value, and vice versa. All right. If you know the R value of something, you can find the U value very, very easily. And you do that simply by dividing 1, all right, 1 divided by U equals R, okay? So 1 divided by U equals R. And if you know the R value and you want to find the U value, it's the same thing, only different. 1 divided by R equals U. So 1 divided by U equals R, and 1 divided by R equals U. And you know what's coming next, right?
Yes.
2 divided by love can only be 1. and 1 is a lonely number. And that's the grassroots 1970. We'll talk about that later. But that's the correlation between the two. So you put all these R values together, divide 1 by the combined R value, you'll get the U value for the assembly and vice versa. Hope that helps. Does that answer the question or the comment? All righty, let's finish it up, and we're just gonna go, we're not gonna go looking through all the charts for the rest of these things now that you know where to find them and what to do with them. So we have our basement windows. Okay, we had a couple of windows, those little basement windows in the upper portion of the basement walls, all right? And those were low E single pane vinyl windows with a storm sash. Those will have a U value of 0.418. Our doors, we had a side door in the kitchen and the front door up front. We're considering those metal doors with urethane cores, no storm doors. The U value is 0.19 for this example. And then we had a sliding glass door, same as a window, really, low E double pane vinyl frame without a storm door. It was 0.361. It's the same basic assembly. So has the same U value as a window would. And then our basement wall, 8 inches of poured concrete, 2x4 studs, 16-inch centers, R13 insulation with a vapor barrier and 1/2-inch drywall. And we looked that up and we find that the R value of the basement wall assembly, including the concrete and Mother Earth on the side, is 0.083. So we look all those up, and now we have them. All right, those are in an easy place to find. Now we can go about actually conducting the heat loss for one of our rooms. So before we get to that, how did we do on our poll there, Dave? And then I want to do our TACO trivia question of the night.
Well, we had about 77% of us that had that answered it, and I will share that with everybody right now, so everybody can see what everybody was looking at. So for the most part, most people were picking around a 67,000 BTU heat loss for the project, and in second place was 55. Third at 81, and then a few of you did 101,000 BTUs per hour. So,
all right.
Once we finish this all up, we'll show the numbers. We'll give you the real number. Yeah.
Very good. Very good. All righty. Let us and then we'll get to that full number by next week, because I want to make sure you guys do the rest of this on your own. But the TACO, we're not going to do TACO trivia for the summer school. We're just doing movie trivia, okay? Because summertime's movie time, right? So we're going to do a TACO movie trivia question of the night for a valuable prize package. And our trivia question for the movie is obviously going to be Pulp Fiction, and you can kind of guess where we're going here. In Pulp Fiction, Vincent and Mia Wallace, they win the big twist contest at Jackrabbit Slim's. The trivia question is, what song did they dance to and who sang it? What song did they dance to and who sang it? Type your answer into the question section, and we'll go through them, and we'll take all the correct answers. We'll put them in a hopper, and we'll pick the winner next week. And what are we going to have for prizes next week, Dave?
Well, let me get this straight for the answer. So they have to get both parts correct.
Right, they have to get both parts correct. The name of the song and the singer, and you have till the end. You'll have till basically 8 o'clock Eastern time to figure it out. So don't be going on YouTube or whatever and just not paying attention to this anymore. See if you just know, okay?
Yeah. Hey, right. John, for correctness sake, there's some doubting your grassroots reference.
Yeah, no, it wasn't Three Dog Night. I see that, Charlie. No, it was the grassroots. You got the wrong song, dude.
Wrong song.
Wrong song. The wrong song. 2 divided by love can only be 1 is the grassroots. 1 is the loneliest number is Three Dog Night. They're 2 different songs.
I've never even gone
with the big dog, Charlie. Stay on the porch, okay? That's just the way it is.
I will never question any music trivia from you, brother.
No, well, there's some. I have big voids in my music knowledge, but there are what I do know. All right.
Mm-hmm.
So no, it was not Three Dog Night. That's a different song. Okay. So name of the song and who sang it.
All right. So
their trivia question.
I am putting together some swag packs. That I'll be sending out to everybody. So we're gonna have different TACO product, not product wise, but shirts, hats, just gear, things like that we have. I will be putting together different packages, and of course stickers too. Yes. Not mail readers. I'll be sending out stickers. Thanks, Rick.
And Rick, did you ever get your stickers, by the way?
That was it.
They did
You
finally
got
get there.
Yes. But also, before we get started again, because we haven't done it in a couple of weeks, we never did week 10 trivia answer or the winner.
Oh, okay. Why don't we,
from-
let's do that
Yeah.
at the very end. All right, when we, after we finish the presentation, when we give this answer, let's pick the winner from last time, right when we give the answer to this question at the end of the presentation. Does that work?
Okay.
Let's do it then. All right.
You got it. You got it.
There we go. So again, what was the name of the song and who sang it? Big twist contest at Jackrabbit Slim's. All right, let's get back to work. And that was John Travolta's big comeback too, after he kind of disappeared for a long time, for most of the 80s. And then he came back in Pulp Fiction and was actually absolutely brilliant in that movie. All righty, so let's get some room dimensions down. Here's our, when you're talking about room dimensions, okay, we need to know length, width, and height. For length, width, and height gives us volume, so we can calculate infiltration. Length and width gives us area, so we can do wall loss, floor loss, ceiling loss, that sort of thing. So generally speaking, you don't have to go crazy with these things. Just go to the nearest quarter foot, so it's, like 7 feet 8 inches is 7 3/4 feet. So it's 7.75 feet, and 7.75 you can multiply, right? And if it's 7 feet 10 inches, round up. All right, it's not going to hurt anything. You just round up a couple inches, call it 8 feet. I mean, those are common sense things to do when you're doing heat loss. If you've got an odd shaped room, you can kind of cut it up into different chunks and get the different square footage areas, or a lot of times people just square it off. If it's an odd shape, they'll just square it off and call it good. Because again, we're doing a heat loss for a house. We're not flying a rocket ship to the moon. So it makes sense to make it as easy as we possibly can.
Agreed.
We're also going to want to know these other things. For each individual room, how many outside walls do we have and which walls are they, so we can calculate those accurately. So we want to know how many outside walls we have for calculating our wall heat loss, as well as calculating our infiltration. And we want to be able to figure out cathedral ceilings. Okay, how do we do cathedral ceilings? Well, you can actually do some geometry and come up with volume and area there, or you can do some averaging. And what I want to do is, just because people have always asked this, I want to just give you a really quick, basically a geometry lesson, if you want to call it that. How do we figure these things out? So here's a room with a cathedral ceiling. All right. So I'm at the peak of the cathedral. I got 14 feet, 8 feet across, 12. So the room itself is 8 feet by 12 feet. My wall to the first level is 8 foot high. And then over here, it goes up to 14. So it kind of goes from 8 feet to 14 feet. Now, there's a couple of things we can do here, okay? First, if we want to do a little geometry, say we want to get the actual area of the ceiling, all right? Well, we know one dimension is 12, but we don't know what that dimension is. We don't know what that dimension is, but we can figure out this dimension here, all right? This dimension here, and we know this dimension. So now we can do a little bit of geometry, courtesy of our old friend Pythagoras. We can do some Pythagorean theorem stuff. So if we want to find C, all right, we go back to the Pythagorean theorem. A squared plus B squared equals C squared. All right, so A is 6, B is 8, and C is what we're going to find out. So we have 6 squared plus 8 squared equals C squared. So 6 times 6 is 36, 8 times 8 is 64, and that equals C squared. 36 and 64 is 100. 100, get the square root of 100, we have 10 feet, all right? So this dimension here is now 10 feet. So now I can figure the ceiling area, 12 feet by 10 feet, that's 120 square feet, okay? So again, it's just simple geometry. We all know, figuring a corner, the 3, 4, 5 dimension, 3, 4, 5, it's 3 squared plus 4 squared equals 5 squared. If you look at it that way, that's 3 squared is 9 plus 4 squared is 16, that equals 25, 3 and 5 squared, okay? This is kind of the same thing, only different. It's 6 plus 8, 6 squared plus 8 squared equals C squared. So we have 12 foot by 10 foot, so our ceiling area is 120 square feet. Now we can also do the same kind of geometry to figure out our wall. Okay, so I know I've got an 8-foot by 8-foot wall here. All right, let's move on to the next slide and we'll be able to take a better look at that. For wall areas, I know I have an 8-foot wall here and an 8-foot wall here, and then I've got 6, and I got a triangle instead of a square here, so I have to figure that part out. So I know 8 times 8 is 64 square feet. So this lower portion here is 64 square feet. I want to find that, and that's basic. That's going to be, again, some simple geometry. I know this is 6, and I know that's 8. It's a triangle, right? So 6 times 8 is 48 square feet, but it's a triangle, right? So I have half of that. So I'm going to simply divide that by 2, and this triangle is, area of that triangle is 24 square feet. I add it to the 64, so this wall right here is a total of 88 square feet. Again, that's one way to do it for wall area and ceiling area. What a lot of people find easier is just to average it all out, all right? Average it all out, square off the ceiling. So I'm only figuring this for my ceiling loss, okay? So in this case, it's going to be 8 feet by 12 feet is going to be my ceiling area. And then by averaging this off, I've got 12 feet by 11 feet for this wall and 8 feet by 11 feet for that wall. So it just, instead of doing a lot of geometry, you just average it off and call it good, because it's a house. It's not a rocket ship. So 8 by 11 right here, that's going to be 88 square feet. 12 by 11 right here is 132 square feet. And then my ceiling, again, my ceiling is going to be 8 by 12 again, and that's going to be another 132 square feet. All right. These are examples of how we would deal with cathedral ceilings. All right, with cathedral ceilings. Fortunately, for our project, we don't have cathedral ceilings, so we're not going to worry about that. What we are going to do is start off, we're going to start sectioning this house. It's basically a logical separation of living areas for how I'm going to do my heat loss. Now, bedrooms are obvious, right? Bedrooms, you've got, okay, here's bedroom 1, right? That's going to be a heat loss area. Bedroom 2 is a heat loss area. Bedroom 3 is a heat loss area, but note I have a closet here, but I'm also including that closet. You know what? It's an interior closet. It's not going to have any heat loss, so don't worry about it, okay? We have our entryway here. Here's our living room, dining room, and then this big family room kitchen's kind of open to one another. Now, you could figure it as one big room if you want to, or you could figure it as 2 separate rooms. That part's up to you. That part's up to you. And then we have our 2 bathrooms. We'll figure those separately. Even though this bathroom number 2 has no outside walls, so heat loss is really minimal, we're still going to want to put some heat in there, because when you're wet and naked, you might as well be warm, wet, and naked, right? So we're going to figure some heat loss for bathroom 2 and put a little something in there. One thing about IBR is whatever you come up with a heat loss, they want you to add 20% to it, and that's the wet and naked factor, okay? So what we're going to do today is we're going to do bedroom 1, and then we're going to do the basement, and you're going to be left to do the rest on your own over the course of the next week if you so choose to. You're going to have the chart, you have all the handouts. Might as well just go ahead and do it, and then when we come back next week, we'll go over it together. So to see how we did. But let's get started. Let's do bedroom 1 together. Now, bedroom 1 together is 12 feet.
Let me just add one thing in there too, John. So
yes, sir.
You know, when I used to do a lot of designs, and I was doing crazy numbers of designs way back in the day, you want to break it out and do every room individually. And right now, this is regardless of zones. We're not concerned about zones just yet. You want to be able to do every room individually so you know what the heat loss is. You want to combine the zones later, fine. Okay. If you want them to all be separate zones, even better. And the reason why I do that too is because as we're looking at bedroom 1 right here, and we're showing a 3-foot by a 2.5-foot window. Well, what if that went and changed? Just that one window, the homeowners came back to you and that changed. Now you have to go find it somewhere in your heat load design that you had done. And if you had done it separately as that bedroom with those associated windows, it becomes quicker and easier. So that's the way I always like to look at it. Don't worry about your zoning yet. You could do it as one big house if you wanted to get a ballpark in the way initial quote designs. But right now, get detailed as much as you can, but individually too. That's the important part.
Hey,
Very good.
Deborah's got clarification on fireplaces. You want to take a stab at that? Or?
Oh, fireplaces. Yeah, fireplaces are always interesting because it totally, first things first, let's look at old fashioned fireplaces with the flue damper. Okay. Um, it's almost all, it's going to enhance the or increase your infiltration heat loss. There's a factor that you can put in here, and I'd have to go look it up. There is a factor to put in there, and Deborah will have it. I'll make sure we get it for you for next week. But you put in a, if you have a fireplace with a manual damper, you will the infiltration will increase dramatically for that area. So you'll have to add that in, and there is a formula for doing that. And we'll go over that next week. I don't have it here, unfortunately. In terms of the wall, depending upon how it's built up, there may be, a lot of brick or stonework, and that might change the conductivity, the conductive heat loss around there. But primarily, we're mostly concerned about what that does in terms of infiltration. Now, if it's a gas log, a gas fireplace that's direct vented, with an automatic damper, then the infiltration's not nearly isn't really of concern. But it is of concern when we get into the old fashioned types. And I'll look that up for you because I don't have it off the top of my head. Dave, do you I'm sure Dave has it off the top of his head because he's that kind of guy.
I used to cheat it, the software, and I used to put in an extra 2x2 window in that space, which would change some of the calculations a little bit, trying to get me to match the BTU load. Like I said, it's been a few years since I've done some designs. Usually the software just had a checkbox that I used if you had a fireplace in that room, and it usually bumped it up 0.1% or 0.1 air change per hour in a space itself. So I'm just doing some looking up right now for it, and I'm not finding it at the moment.
Hey, John.
Okay. Yes, sir.
Charlie McCracken's asking about a specific Rhode Island building code, or like plan review. Would they accept this procedure? I think that's going to be a local basis. A lot of people want their heat losses to fall within a certain criteria, and that's going to be from state to state, area to area. So unless you want to add anything to that question, so
specifically for Rhode Island, don't know, Charlie, if it is accepted. I know a lot of code jurisdictions require something done by manual J. All right, it has to be a manual J compliant heat loss calculation. Here's the thing about heat loss calculations, Charlie. They all use the same arithmetic. Okay, every last one of them uses the exact same math formulas. All right, and they're all the math formulas we're going to see here. It's just a matter of what kind of different factors are put in. Manual J is an interesting book. It's about that thick. All right, it's about that thick, and there's nothing more in there for residential applications than what you have in the packet that I just sent you. It's all just other stuff for different types of commercial applications and different circumstances and things like that. And Manual J has about 17 different addendums, manual H, LMNOP, and all that other fun stuff. But for some reason, it is because it's blessed by the engineering community. It tends to be the standard. So as far as this specifically is concerned, I couldn't answer that question for you for the local code in Rhode Island for permits. I do know if the IBR is kind of the basis of virtually any software too that you might use, whether any heat loss calculation software. It's all based upon the same stuff. So I would ask the local jurisdiction if they will accept an IBR/AHRI heat loss calculations. And then if they say no, I'd ask why not. Because if they say it's got to be manual J, then it's got to be manual J. Okay. But heat loss is heat loss is heat loss. Just the same thing. Okay. Is that right? So let's go work through bedroom number 1 here. Okay. So our dimensions for bedroom 1, first thing we're going to do is just get some information in. It's 12 foot by 12 by 12.75. 12 feet 8 inches is 12 3/4 feet. And we have 9-foot ceilings as we specified earlier. So 12 by 12 and a half, 12 by 12 3/4 by 9 foot high. How many outside walls do we have? Well, clearly we have two. We have one 12-foot wall and one 12-foot 8-inch wall. Those are both outside walls, so that's important information to know. And then we go and we fill in the form. Now, this heat loss form is also in your packet, and it's every room. You know, just you put in the room, then you start putting in the length, width, and height, and all the basic information that you have, and it's all mathed out right here for you. So bedroom number 1, we put in the length, width, and height. 12 by 12.75 times by 9. Next, we put in our indoor design temperature and outdoor design temperature. 70 is our indoor, 7 is our outdoor. Next is our design temperature difference, that's 63. Now, exposed walls, there's two little number insignias there, or symbols. They want to know how many 12-foot walls and how many 12 and 3/4 foot walls do we have for outside walls. You know, if it's got 2 outside walls, 1 outside wall, etc. So we know we have one 12-foot wall and one 12 and 3/4 foot wall. That's going to be important in a second. All right. So we have all of that information. Now we're going to start with infiltration. And if you look at line 1, infiltration, we're going to use the volume of the room above grade only. Now the whole volume of bedroom 1 is above grade. So the first number we want to find, that we want to put right here, is volume, length times width times height. Well, we have length times width times height right here, right? 12 by 12.75 times 9. All right, now infiltration is a basic math formula. It's the volume of the room times the infiltration factor times your design temperature difference. All right, design temperature difference. Now, what's an infiltration factor? Well, it's a number IBR gives us to help us estimate the heat loss. There's a bunch of different tables, okay? This is table 2. And they give us heat loss factors for different types of construction. They give us 3 sets of factors. All right, the first one is for infiltration heat loss factors for windows and doors not weather stripped and no storm sash. So it's kind of an older, looser home, not an uninsulated home, but not your premier construction. All right. Next, you have infiltration heat loss factors where the windows and doors are weather stripped or with a storm sash. And then the third set of factors, that's for your old farmhouse where you can actually see through the walls, for goodness sakes, okay? Really, really high infiltration, all right? Really high infiltration. So they give us a bunch of factors. So we got room for first, we're gonna be using the section 2 here where the windows and doors are weather stripped or with storm sashes. All right, and we see here a room with windows or doors on one side only. So that's one wall with outside windows and doors, or one outside wall with windows and doors. That's 0.012. 2 outside walls with windows or doors with openings. That's 0.018. And then 3 outside walls with windows or doors, or the main entry hall. We got 0.027. And a sunroom with many windows and 3 sides is 0.036. So this covers you through a lot of different possibilities here. Now, what do those numbers represent? 0.012, 0.018, 0.027. Well, all of these numbers represent air changes per hour, estimated air changes per hour. So 0.012 represents 2/3 of an air change per hour. What IBR is figuring here is a room with one outside wall with openings, okay, with openings, one outside wall with openings. We figure there's going to be, over the course of an hour, 2/3 of an air change, meaning 2/3 of the heated air in that room is going to leak from inside to outside and be replaced by cold outside air. All right, so that's so that's 2/3 of an air change per hour. If I had 2 outside walls with openings, that's 1 air change per hour. 0.018 represents 1 air change per hour. All of the air is going to leak out over the course of an hour, be replaced by cold outside air that we got to heat up. And 0.027, 3 outside walls, or 3 outside walls with windows. Then we're talking 0.027, or about 1.5 air changes per hour. All right. These numbers actually represent the number of BTUs. 0.012 is the number of BTUs needed to raise 2/3 of a cubic foot of air, 1 degree Fahrenheit, 1 hour. 0.018, the amount of BTUs needed to raise 1 cubic foot of air, 1 degree Fahrenheit, 1 hour, and so on and so on. So that's how these numbers work. For our job, we had 2 outside walls with openings. So we had 2 outside walls, and each wall had an opening. So we're going to use 0.018, 2 outside walls with openings. That's our factor. So we're going to go back to our chart and put in our numbers. 12 by 12.75 times 9, that gives us 1,377 cubic feet of air volume in the room. The factor that we're going to use, all right, our infiltration factor was 0.018, and the design temperature difference, as we see here, is 63. So we simply get out your calculator and multiply that out, and what do you got? 1377 times 0.018 times 63. That'll give us an infiltration heat loss of 1,562 BTUs. Piece of cake, all right, piece of cake. Any questions there? Anything that doesn't make a whole lot of sense where we go? All right.
Comments, but no specifics. See anything, Dave?
Well, here's one from Mark Sheen. 0.018 is the number of BTUs to raise the temperature, and how much air? 1 cubic foot. It's the amount of temperature. It's the amount of BTUs needed to raise 1 cubic foot of air 1 degree Fahrenheit in 1 hour. There we go. There we go.
Or 2/3.
No, 2/3 is 0.012.
Gotcha.
There we go. All righty. So there's our infiltration heat loss. Now, these factors, it's interesting. These factors were put together by IBR based on some test homes that they built. All right. People always ask, well, what about wind? Does wind affect infiltration? It sure as heck does. But see, there's so much fudge built into this heat loss. Okay. The infiltration factors that IBR uses were based on test houses that were built, and they're based upon a 25-mile-an-hour wind blowing in all 4 directions at the same time. I don't know how that could happen, or if it did, which way your hair would blow. But you want a little bit of fudge. There's a big old slice right there. So it's based on 25-mile-an-hour wind blowing in every direction. So yeah, wind and wind direction is taken into account for infiltration in these calculations. All righty. Sealing loss, it's area. So it's area times U value times design temperature difference. So now we don't have to do volume, we just do area. So 12 by 12.5. If it's partially exposed, we only calculate the sealing loss for the partially exposed area. We do a little bit of subtraction, all right, do a little bit of math that way. But let's fill in our numbers for the sealing loss. In our case, we're filling, the whole thing's got a built up attic. So let's put that information in. So 12 by 12.75 is 153 square feet. Our U value from our sheet that we figured was 0.02, 63 degree design temperature difference. That's going to give us a sealing loss of 193 BTUs. Okay, not a lot, 193 BTUs. Okay, that's where a lot. It's where your insulation really comes in handy. Now for floor and slab, well, it's not a slab, so we're not doing a slab loss. It's over a heated basement, so the basement is going to be heated. We're not going to do a floor loss here. So what we're left with is windows, basically, for this particular bedroom, windows and walls. So let's take a look at our window load. Now windows, we simply add up the window area. So I've got 2 windows. One window's 3.5 by 2.5, and the other window's 3 by 2.5. Now, presuming they're both the same window, and we didn't see anything in our spec sheet that said they were different, presuming they're the same window, we can just figure the area of each window and add them together and just do the math once. We don't have to do each window separately. So 3 times 2.5, that's a 7.5 square foot window. 3.5 times 2.5 is 8.75 square feet. Put them together, we've got 16.25 total square feet of glass in that bedroom. So we only have to use that number. We don't have to do this math twice because of the same window. You're going to have this. If I do it twice and add them together, it's the same thing as adding them together and doing it once. Okay, so there's no real difference here. Then we find the U value, which we already did. It was a low pane double E window, and we put in our information. So for the window, our total window area was 16.25 square feet. Our factor was 0.361, and our design temperature difference, of course, remains 63. We math it all out, and we come up with a window load of 370 BTUs. So,
John, can I make a statement on the window thing?
Please do.
You know, if you're just doing this type of format and no one's going to do plan review of your takeoff, what John was talking about works faster and better. Where I've run into problems when combining windows, when somebody's looking over your takeoff, They're counting windows, and then they're counting your windows, and they're coming up with different numbers, and it could save you a callback. So again, just a suggestion to do them individually if somebody else is going to be reviewing your set of prints.
Very good, very good. Question from Gerald: is the window calculation based on the rough opening or the actual glass? Generally, I just do, it's the interior dimensions, not the rough opening, but the interior dimensions. For example, I mean, I'm looking at my window right now, and I got a side here, a sash here, and a sash here. It's just that you can't see it. Well, sure you can. All right, here we go. It's from here to here. There's my dimensions from there to there. All right, and then from the sash up to the top. So it's an interior measurement. Okay. Yeah, sash size. That would be the way to go with it. That would be a better way to explain it, Eric. Thanks. So, and that's how you would do that. Now for walls, again, walls, it's the same as before. Okay, we add up the exposed wall areas. Now this case, again, if someone's going to review it, maybe you might handle it differently, but it's an outside wall. I just figure one big outside wall. I got a 12-foot wall and I got a 12 3/4-foot wall. Let's just call this one big wall, shall we? All right, it's 24 3/4 feet long. It's one big outside wall. We'll make it one, just add them together. It's one big outside wall, 24 3/4 feet long and 9 feet high. Okay, it's 24 3/4 by 9 feet high. All we have to do then is deduct the door and the window areas, and we'll have our net wall area. All right. So let's take a look. Okay, 24.75, 24 3/4 times 9 feet high. That's 222.75 square feet. But we want to take that 16 1/4 window area out. Okay, we subtract the window area, and that's going to give us 206.5 square feet. Right, 206.5 square feet. Our wall factor that we looked up earlier was 0.058. Design temperature difference was 63. Multiply that out, we're at 755 BTUs for the wall. Now, let me ask you this. Do we have to be concerned about orientation, north, south, east, west? Do we have to factor that into this wall loss? You guys tell me what you think. Does that need to be factored in for wall loss? Okay. How do you factor that in? Or do you need to? Daniel says no. Jimmy DePalma says no. Okay, and you're right. It does not need to be factored in at all for heating. For cooling, it does. For heating, it doesn't. For heating, it doesn't. Because
Bill got that one right. Yep, he says only solar gain. Yeah.
Only solar gain. There's no such thing as lunar gain, and if there is, I don't know how to count for it. All right. And when it's coldest out, it's dark. It's at night, and the house doesn't know which direction it's facing. So yes, we care about orientation when we're doing cooling loads. No, we don't care about orientation when we're doing a heating load, okay? So we've pretty much got everything here, man. We've got everything here. Let's add them up, all right? 1562 for infiltration, 193 for ceiling, 370 for the windows, 755 for the walls. That's 2,880 BTUs for that bedroom, all right? Good, we got a room done, all right? We got one room done. What I'm gonna ask you guys to do next week, for next week, is just do the rest of the house. If you're so inclined, do the rest of the first floor. All right, you add 20% for each bathrooms, etc. But just do the rest of the house and see what you come up with. See what we have.
Homework.
Say again.
Yes. Homework.
Homework. Yes, y'all
for
get
summer school. We hated that.
Some summer school homework. God, that was kind of nasty of me to do, wasn't it?
Yeah,
it was. But I will sweeten the pot, John. So I will have a special prize for those that do give us some numbers. Yes, and then I will do a
special. That's special.
So
if you get us the number, you get us the number next week. I will do a separate raffle for that. So yes.
Oh boy. So if you go ahead and do this and you get reasonably close to the number that we're looking for, and you tell us next week, hey, there'll be an extra little something in it for you, quite possibly.
That's right.
Now, I want to do the basement really quick, all right? For infiltration, as we said, you only calculate the wall space above grade. And if we take a look at this, we're seeing that there's really only two walls above grade. see the two walls where there are windows? Those are going to have a portion of the wall, really 1.5 feet of each wall is going to be above grade. The other two walls are below grade. You got the garage on one side and then, everything, below grade on the other side. So we do have some outside walls that we have to contend with, and we have two outside walls that are in fact above grade. So what we're going to do is two separate heat loss calculations for the above grade wall and the below grade wall, as well as the floor. And there's a special way to do floor loads below grade. Okay, so let's take a look real quickly. All right, we put in our information. Okay, the length and width is 55.5 by 25, and it's only a 7.5 foot tall ceiling. Our design temperature difference, of course, is 63. Is 63 degrees. For infiltration, only the volume above grade, right? So that's 55.5 feet by 25.5 feet, all right, by 1.5, all right? That's the part above grade. So it's a very small amount of volume, 2,081 cubic feet, all right? Our factor is going to be 0.018 because there's two outside walls, right, with openings, and 63 degrees is our design temperature difference. So our infiltration heat loss for the basement's 2,360 because it's big, all right, but it's only, it's long, but it's only 1.5 feet, all right? It's only 1.5 feet. No ceiling loss, of course, no floor loss, but we do have to do a slab loss, okay? We do a slab loss for our floor, okay? So for our floor is a basement slab, all right? If we were on grade, we would do perimeter. If this was a slab on grade, we'd do perimeter in feet. So it would be 55 plus 25 plus 55 plus 25, because we'd have outward heat, we'd have heat loss, through the exposed edge. This is below grade. It's simply area, the floor below us, 55.5 by 25. The U factor for the basement slab, okay, we're going to use 0.04. We'd look that up, 0.04 for the floor load in the basement, 63 degrees design temperature difference. Now we got a 3,500 BTU downward load in the concrete slab floor. All right, concrete slab floor. The windows are itty bitty. All right, there's 6 windows. Each window is 1 foot by 2 foot. All right, times 6 windows. So that's 12 square feet of glass. Single pane, wood with a storm sash. Okay, that had a U value of 0.418, 63 degrees. All right, 316. Okay, now for walls, we've got some area that is above grade and we've got some area that is below grade. Okay, some areas above grade, some areas below grade. So we're going to figure this out. I've got 161 linear feet that are above grade. All right, 161 linear feet above grade. And so that comes out to 241.5 square feet. Subtract the windows, we're down to 229. That gives us a U value, with our U value of 0.083, 1,200 BTUs lost for the exposed above grade portion of our walls. And then we have our below grade portion, okay? That's 161 times 6 feet, 966 square feet, with a 0.046 U value, again below grade with the Mother Earth, etc. And that's going to come out to about 2,800 BTUs. Again, you look all these things up in the booklet, in the charts, and you'll be able to find where all these numbers come from and how we came up with them. All right, so our total for the basement is 10,173 BTUs. So just a couple of little things you got to do with basements. The infiltration, use the above grade portion only. Understand how to do it for a below slab. It's simply floor area times your factor. So it's kind of like a normal floor. And then for your walls, you've got a portion of the wall that's above grade and a portion of the wall that's below grade. So you'll have to be able to figure out the load for both for those areas. Okay. Do that separately, then you add them together, and bing, you got your basement load, 10,173. All righty. Now, our trivia answer. Our trivia answer. I saw a lot of people got this. All right. A lot of people got this. The answer is, of course, by Chuck Berry. It just goes to show you never can tell. All right. A terrific, terrific song. And Vincent and Mia took home the prize, and then Mia, of course, had a rough trip home. But anyway, that's kind of where we're at for our trivia answer. And anything that comes in after 8:02 p.m., you're not eligible, but everybody got it in, so we'll pick a winner for that next week. All righty,
That's right.
got a lot of questions here, but I think we do want to get to the winner from week 10. Do we want to go do that one now, Dave?
We sure can.
All
If you
right.
want to share my screen, let me share the screen.
I'm going to make you the presenter, and there you
Okay.
go.
All right, let me, I hate when it does this. I got to change the screens.
While he's doing that,
Hang on a second.
Benjamin's got a question
Okay.
about doing the load on the first floor. And since that basement was going to be heated by the same product, by the same heating equipment, and it was going to be the same temperature, there's no downward loss in that sample project that we're doing, Benjamin.
Right. And here's another thing about floors with IBR. If you're over an unheated, unconditioned basement, all right, IBR will still say don't bother with a floor load on the first floor because it's not 0 degrees or 7 degrees in the basement. It's more like a controlled 55. So your design temperature difference is 70 to 55, and it's only 15 degrees. If you were actually to math that out, the load would be more than overcome by a person walking into a room. So IBR will say, hey, you don't really need to do a floor loss if it's a full basement. If it's a crawl space that's like a mini basement that's fully enclosed, you may not have to do a load then. If it's a ventilated crawl space where the temperature in the crawl space is close to the outdoor temperature, well then yes, absolutely do a floor load in those examples.
Awesome. All right, so last time, week 10, one of the question that we had was Taco manufactures circulators in Cranston, Rhode Island, as well as circulators. We do manufacture some pumps also up in Milton, Ontario. But where in Europe do we manufacture circulators? Was our question, and the answer was Taco Italia, which is in Sandrigo, Italy. So these are the names of the people that had answered that correctly for me on week 10. So, and what we are giving away, since week 10 was about domestic hot water recirc systems, we are giving away a HotLink Plus E, the
Nice.
full package. Yeah, where you've got the
Nice.
60 circulator cord, you've got the smart plug, and you've got the HotLink valve in there. So let me click to spin. Where's my mouse? There it is. And let's go. Let's see who our winner is. And must be your cousin, Rickster.
Well, no, he's D Mayo. I'm just Mayo, right?
You're A Mayo, he's D Mayo.
D Mayo. He's the man.
So Peter, let's say I don't see you on tonight, but I will have to give him an email and let him know.
Cool.
So excellent.
Cheers.
Thank you. And let me get back to stop sharing and give it back to you, JB.
All righty, thank you. So am I the presenter now? I am the presenter now. Show my screen. Okay. And let's get this guy back up here. All righty. Very good. Well, with that, want to go over what are we going to talk about next week, because that takes care of this week. For next week, we're going to finish this heat loss. We're going to size up radiators, and we're going to do zone layouts. We're going to see if we can partition this this setup for a nice big zone system. So that's what's coming up next week. But right now, what we're going to do is, if you want to launch that next poll, Dave, we want to crowdsource for our topic. We're going to spend 20 minutes discussing this project next week. Okay, so 20 minutes is going to be spent on this project next week, and after that, we're going to do a future. We're going to let you guys pick. All right, these are the topics at hand. So what I want you guys to do is just pick which one you want for next week, and we're going to do this every week. Every week, you're going to get to pick the topic that we discuss next week for the bulk of the class. So go ahead, that poll is now open, so you guys can pick what you want. and we'll see how we do here. And we're also going to leave this on Facebook and et cetera, and see where we're at in terms of a presentation. And we will have we'll put together that presentation for you for next week. So the rest of the week, we're going to have those on social media so people can vote there. And then when all said and done, that's our topic for next week.
Right.
Now,
and also, there will be a survey when the class is over, and you'll also get a copy of that survey on the follow-up email too. And that survey is going to just quickly, a quick answer out of the 3 that I show you here. If there is something else you would like to see, please let us know so we can start including that in the selections coming up in the future. So so make sure you pay attention to that survey at the end of tonight and also in the email that you'll get tomorrow. So thank you so much for that to help us get this rolling for what you need to get out of it more than what we need to talk about.
Very good, very good. And I just got a text from Rick. He's got family visiting and he has to cook dinner. So he's kind of leaving us. So it's just going to be us guys here for the remainder of our time together. And again, we still have those stickers. So if you want some stickers, contact Dave.
They don't see that yet, John. It's still on the poll.
Oh gosh, yeah. We're still got.
So I got
about
just about 67% of people out there that have voted so far. We're going up there. So 2 minutes into it, and I'm gonna kick it out. So greatly appreciate you guys that have. Like I said, you can still put in some questions in the survey or answers into the survey. So I'm going to close out this poll right now, and that is it.
All righty, very good. So it looks like water quality is in the lead. We'll see how this works out for the remainder of the week. So what we'll do now, again, the slide up now just says, hey, if you want some of these Takeo After Dark stickers, Dave has a boatload of them. Contact Dave at Takeo Training on Instagram. Just send him a private message or direct message on Instagram, and Dave will get you some, and give him your address, and Dave will get you some stickers. And if you have your own stickers, Dave just loves to swap. Okay, he's a sticker swapping son of a gun right there.
Got a bunch on the wall behind me, so thanks to the guys that have sent them out to me, and I'm adding some more and be bringing them up to the factory and setting them up on our toolboxes in the training center also. So
excellent, excellent. All righty, well, I'm going to close off the screen sharing, and let's get to the questions, shall we? Because it looks good. Like we have a bunch here to go over.
We did. I do want to bring up right away, one of the last questions just came in from Nick, had asked about, will the webinar be online later? Yes, it will be. So we will, in the email that you'll get tomorrow, you'll get a link to watch it again. If you want to watch it elsewhere, it's going to be uploaded to YouTube on Mechanical Hub's website, YouTube page, as well as our YouTube page. So, so you can go and watch it again. If you miss us that much, or you want to share it with your friends and family, because how many of our family members actually know what we do for a living, huh? they have no idea. So yeah, they can go and watch this stuff and see what we do.
There you go. There's a question here from Dom Spatafora about, can we get a copy of the presentation slides? Unfortunately, we're not allowed to give those out. We're not allowed to give those out. We're not allowed to give the slides out. But again, you will get a copy of the video or recording that you'll be able to view as many times as you need to. So you'll have a link to view it online. It'll be on the Mechanical Hub YouTube page. It'll be on Takeo's YouTube page. So there'll be all kinds of spots where you can go ahead and view the presentation. So, but unfortunately, I wish we could give out the sites. We can't. We're not allowed to. So there we go for that. What else do we have for questions? There's a whole bunch of them. Boy,
there was one that came in a while ago, so I don't want to forget it. So Alan had asked, how do you account for a through-the-wall air conditioner?
You mean like a mini split or something like that?
I would assume no. I'm just assuming a window shaker that you permanently install. That's my thought. That's my guess on what Alan's
Wow, that's a really good question.
Yeah.
Is that what we're talking about? A permanently installed window air conditioner. That's going to be weird, man. That's weird. I mean, that's going to boost the infiltration considerably. It's almost like leaving a window open. So I'd pick a really, at that point, I don't think there's an exact formula for that. You're going to have to pick a high infiltration rate for that one room, because it's like having an open window, more or less. the flippant answer is take it out, and close the window in the wintertime. But hey, if you do mean like a Mitsubishi or one of those one of those mini splits that are installed, again, those are generally sealed up pretty well as part of the equation. So I don't think it's going to affect the infiltration all that much. Okay?
No, you're just looking at a line size. You're just looking at a hole that's going to get sealed in the wall after that. So you're good there. Yep.
Yeah, I'm not sure it's going to have that much of an effect on infiltration. We've had a lot of people in the past ask, well, what about if I have a heat recovery ventilator or an air-to-air heat exchanger for for fresh air to keep to keep air? How does that affect infiltration? Actually, it lowers infiltration, because what you're doing is you're mechanically controlling the air changes. You're mechanically controlling the air changes. You're not letting nature do it. You're controlling it mechanically, but you're also tempering it, because you're not bringing in cold air. You're bringing in tempered air. So what I usually do with that is I just figure infiltration straight, knowing that with an air-to-air heat recovery ventilator, I'm going to be more than fine. It's not going to that's not going to make infiltration worse. It's going to make infiltration better. All right. So that's for that. That's kind of how I would handle it. All right, kind of scrolling back here with some other questions. There's a whole bunch here. Boom, 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 boom. On the first floor. Okay, we went through that one about the heat loss through the first floor. Will under slab insulation affect the floor loss? And what about open cell insulation and block walls? Well, yeah, both of those would be taken into account when selecting your infiltration, when selecting your U values for both the floor and the ceiling, taking into account both of those. So that would just be based upon the number that you choose for your U value or infiltration factor. All right.
Very good. And the charts that we're sharing with you, these were made quite a few years ago, so they may not have some of the newer insulating values that we're used to today with the spray foam and whatnot. So this is an older worksheet, but you can still find those numbers and still apply them appropriately too.
Very good. Yep. Let's see what else we have. Just for everybody's knowledge, Robert Bean recommends never having more than 40% glass area in a wall for high performance buildings. Well, yeah, I mean, it's great to have a lot of glass so you can see outside, but people outside can see inside. And if you're doing something you don't want people outside to see, you shouldn't have that much glass. But hey, that's my life in a nutshell. But yeah, I mean, Windows just don't have the same R value or the same U value as a wall. So you're going to have more heat loss, both in terms of infiltration and in terms of window loss. So yeah, keep it to a minimum. Keep it within reason. Okay, to keep your
and stop and think about this for a second, too, guys. The window or a wall is a minimum 10 times the R value of a window. Right? It's more insulative than a window is. But here's also that's interesting, because I used to do a lot of radiant designs, and we had limitations on how much heat you can put into a space when you do a radiant floor. So if you're designing a project, and let's say this is a new construction, new house, one of the things that we get to do is to make a recommendation. Let's say you had a project and the homeowner wanted to put in, the wide plank pine wood floors. And the limitation there we're looking at is 78 degrees, but they also have this whole wall of glass. And now instead you're saying, all right, well, I can't heat the room with the radiant floors because I'm going to make the floors too hot, and I'm going to buckle the floors and they're going to get destroyed. So we have to put supplemental heat in, a second stage. Well, this is what's interesting on what we get to do here. We can turn around and say, well, what if we, instead of spending the money on a secondary heating source for this space, you spend the money on the glass and make it a triple pane and lower the heat loss of the space. So this is where we can be their energy consultants rather than just the guy slapping stuff in their house. So that's also something to think about when we're doing these heat loads for people.
Very good. Very good. Here's an interesting question from Daniel Leary. Could you discuss using radiant heat in the main floor, working to heat the basement as ceiling radiant heat, and the main floor radiant heat through the floor? So basically putting in one layer of tube and having to go up and down. Good question, Daniel. Damn near impossible to do. because you would have to have exactly the same R value above as you do below. And I don't know how you're going to do that. And the other thing is, I don't know where you're going to put thermostat. Do you put thermostat downstairs or upstairs? We used to get this question all the time back in our Worsbo days, because, oh, it would be less expensive that way. He says, yeah, it would be. It also wouldn't work.
Yeah. You got to steal from Paul to give to Mary. Yeah.
Exactly. Because you're going to have the exact. I mean, not a digit over. One of the R value above and the R value below would have to be absolutely the exact same. Okay, so there won't be. It wouldn't be easier for the heat to go down than up. Right? Man, heat's lazy and stupid, right? Heat's lazy and stupid. It just takes the easiest path in whatever direction it gives it the least resistance. Okay, everybody thinks heat rises. Well, heat doesn't rise. Heat transfers from a warm surface to a cooler one. If it's easier for that heat to go down, it's going to go down. If it's easier for the heat to go up, it's going to go up. If it's easier to take a left and go out the side, that's what it's going to do. So to get one layer of tube, if you will, to heat both upstairs and downstairs is essentially impossible. It
Right.
really just can't be done. Both in terms of BTU carrying capacity of the tube, number one, and number two, just from a practical standpoint. So I hope that addresses your question, Dan. That's a good one. We get that
Yeah.
all the time back in our work.
And it's the same thing. It's the same question, just worded differently. Well, I don't want to put insulation in underneath my radiant floor down in the basement space that's heating the first floor. Well, all that heat's going to come down first, especially if you do an underfloor style system, because the R value above the tubing is going to be higher than below the tubing. So you need to, and some people say, well, I don't want to do that. Well, you're going to get the basement to about 95 degrees before you start getting heat upwards, which you don't want to do. That's just a waste of energy. Unless you wanted the basement to be 95, then that's another story, and you've got no control of the heat upstairs. So, yes. It's hard to do that, Dan.
Very good. Very good. All right, keep your questions coming in, guys. This is from Newport, Rhode Island. It doesn't really go below 9 degrees. So what does the 5800 mean? You're looking at are you looking at the degree days? That number, the two numbers on the in the outdoor design temperature chart. The first number, the small number, is going to be the actual design temperature, all right, that you would use. And then the second number is the number of degree days
Yes.
anticipated for that area, and you use degree days to help you figure out fuel consumption. All right, and we can certainly do a fuel consumption session later on. We'll put that on the list, Dave, for our upcoming polls. Do you guys want to do one on fuel, how to calculate electrical consumption, how to calculate fuel consumption? Because that's really actually helpful if you're trying to sell an upgraded system and you're offering them like standard efficiency and high efficiency. You can actually show them, okay, this is what it's going to cost you to run it, your standard efficiency system, compared to last year. You always want to compare backwards. You don't want to predict the future, because you can't. All right, because if you do try to predict the future and you're $15 off, they're coming after you for $15. Always compare to what you had last year. If you had this equipment last year, here's what you could have spent. If you had the standard efficiency upgrade or the high efficiency upgrade, and then you can make the call based on the numbers. So that is and that's how you use the degree days. There's a math formula for that. You get into the millions, and there are sources out there where you can actually find more accurate degree days than what you see here. So there's a lot of different things that you can do based on real actual data, because you always want to look back instead of forward. So I hope that helps. Daniel,
I do want to point out also
Yep.
about doing heat loads too. So, and a lot of stuff what we showed today, you may have to get the blueprints and the new windows that were installed in a house, maybe if it's an existing home. If this is a new construction, all right, you're going to get those blueprints. But I do also know a friend of mine, he's not here now, he was online earlier, that has his own way. And I got to refresh my memory on how he does it, but what on doing heat loads or finding the heat load of somebody's home, where he looks at, the last bunch of years in their fuel bills too. And there's other calculations that he's done, but there are other ways to get kind of close to what your heat load of somebody's house is going to be. So don't, and as we started off the day, all the math ends up being the same anyway, right? It all comes from the same location, so to speak. So there are other ways to to get your numbers, so to speak.
There you go. There's a question from Curtis about, I guess going back to radiant heating. Could you use 2 layers of tube with insulation between them for do the first floor and then the basement? Oh, absolutely. Yeah, absolutely. You could do radiant floor, you know, between the floor joists to heat upstairs, put your insulation in, and then you could do radiant ceiling to heat downstairs. The thing about radiant ceiling for concrete slabs, for basement slabs, all right, remember that basement slab can be a heat sink. This is one of those instances where usually when you're talking about radiant heat, you want as low of an R value as possible on that floor so it's not much of an insulator. Well, since we're going from the ceiling down, you want to go El Crazio on a carpet and pad R value down in the basement, because you don't want to let that slab absorb heat. If it was just going to the bare slab, that slab would absorb that heat. You'd never really heat up that area like you'd like to. So under those situations, that's the one time you want to go absolutely crazy with a high R value pad and a high R value carpet in that basement to act as a barrier so the slab doesn't absorb all the BTUs. But other than that, yeah, radiant ceiling, I got to tell you, radiant ceiling is one of the great underutilized radiant heat sources going. It really is, because you can get very high BTU per square foot outputs. You know, with radiant ceiling, you're not really worried about the surface temperature, because unless you have really weird personal habits, you're not spending a lot of time in contact with the ceiling, right? So you can utilize that. And the other thing about radiant ceiling is it's a very low mass system. It's a very low mass system, so it responds very quickly. So think about areas where you might want quick responding heat and using radiant heat. Like maybe you got radiant heat in the rest of the house, but the bedrooms, okay, maybe they're going to put a nice little carpet and pad in the bedrooms, all right? Well, you do want something that's going to respond very quickly in the bedrooms, right? You want something that's going to respond very quickly. So how about doing radiant ceiling in the bedrooms? All right, you go to bed at night, you turn the thermostat down, it gets cool. You get up in the morning, turn it up, it heats up pretty quick. All right, perfect spot for quick responding low mass heat. So radiant ceiling to me is a great underutilized radiant heat source. Okay, and Keith O'Malley said, John, that's a great statement. Boy, tell me what it was. I'll do it again. I love it when people tell me that. Tell me what it was. I want to do it again. Oh, great to mention radiant ceiling.
Yes.
Thank you, Keith. Yeah,
yes.
It really, and it's easy to install. You know, you can use aluminum plates. Just put, insulate, put aluminum plates, and it comes right down. You know, there's actually a company in Italy that makes this thing called the oh God, what is it called? It's called Radiant Ray, I think it is, but it's a 4x8 sheet of insulation. All right, 4x8 sheet of insulation with metal plates built into it, aluminum plates built into it, and 3/8-inch tubing built into it, with a header that you can do quick connects and put these 4x8 sheets together, screw them to the ceiling, snap the tubing together so it's continuous. And then it also comes with a piece of sheetrock as part of the assembly, and the sheetrock has the tubing pattern laser engraved on it. So, if somebody below you, is screwing, the guy is screwing things into the ceiling, they have a map of where the tubing is. So at that point, the only excuse he has for putting a hole in your pipe is that he's a freaking nitwit, all right? And these things, and the output in terms of BTUs per square foot is just insane at really low water temperatures. It's not inexpensive, but I know a guy in California who imports it and puts it into the houses that he builds out on the coast. Very, very inexpensive. He runs them off a water heater, for goodness sake, because you can. And it's perfect for an area that doesn't need air conditioning, and the heating loads aren't great, but it's a long heating season, just not a deep one. And it works just fine for that application. Cool.
And you start looking at basement spaces. Radiant floors are kind of difficult unless you're pouring a slab. All right, but if you're going to retrofit radiant and try to put it into the floor, I find it's totally not worth it, because I did that at my own house. So when I started working in the radiant world and I bought a house and I was retrofitting and finishing off the basement space, you don't feel the heat's on. So the extra work and the raising of the floor and everything that I had to do would have been better if I had done a radiant ceiling or a radiant wall, for that matter, in the basement space. So yes, you get a lot of flexibility when you take it out of the floor and do what you want to do with it. So the only limitation that I found is 120 degrees surface temperature of the sheetrock. So once you start going above that, you start degrading the sheetrock itself. But if you need 120 degrees on the surface, we got to talk. Yeah.
Yeah.
Close the
we got
door.
issues.
Yeah.
We got issues. Yeah. Close the door. Close the door. That's right. That's right. Again, we used to teach radiant sealing, and people would say, you know, well, that's silly. Heat rises, right? Well, no, we went over that. Heat does not rise. If heat did in fact rise, we're all in serious trouble, because where did God put the sun? Up in the sky. Oh, if heat did in fact rise, we're screwed, because it's up, right? We're not getting there. If heat did in fact rise, why is it colder at the top of the mountain? Let's just think about these things, okay? Let's think about these things. In an enclosed space, it's heated air will rise, cool air will fall. It's a density thing. We're talking about heat as an energy ray, if you will, and it just transfers from a warm surface to a cooler one every single time. Heat doesn't rise, people. Heat doesn't rise. I remember seeing actually a promotional brochure printed by a radiant heating company. The first thing it said to say how great radiant floor was: heat rises. Everybody knows that. Well, no, not the person writing that brochure. They didn't know that.
It's just semantics. Yeah. A lot of times we know what we mean. It's just sometimes semantics too. But there are some people that will always say that that heat rises. Yes.
Yeah, there we go. There we go. Is that right? Yeah, and another truism about radiant floor heating and a retrofit into a basement, it is. I've yet to see a case where this was not true. So I'm going to say, in my experience, David, you might have different experience, but in my experience, in 100% of the applications that I have seen, it is faster, easier, cheaper, better performing, more effective, more efficient, and simpler for everyone concerned to install the tubing into the slab before the slab is poured. All right. Before they pour the slab, it's the best way to do it. You wait till after the slab is poured. Putting the tubing into the slab is very difficult. Do it before they pour the slab. Everybody's happier. All right. Everybody's happier. So this is kind of a trip down memory lane for us, isn't it, Dave?
Yeah. I remember back in those days, there was somebody developing a concrete saw to cut channels.
No.
Oh yeah. Oh heck
Lord.
yeah. Somebody was developing a tool to cut the concrete so they can put tubing in. And I was just like, no. Yeah, don't do it. Don't do it. I don't think it went anywhere. I know a few guys put them in or tried it, but I don't think it went anywhere after that. Yeah.
Oh boy. I saw this question from James Petreka about heat moves via convection, conduction, and radiation. Yes, they do, in varying degrees. I have before me the Bell and Gossett Hydronics Design Handbook, and that design handbook was published in this was published in 1949. Okay, it's the second edition. It was published in 1949. It's an interesting book, and great job by the guys at Bell and Gossett. Now let me find what I'm looking for here. That's this one right here, because that's where the bookmark is. All right. And they're talking about radiant heating. All right, radiant heating, and they talk about the behavior of heat and physiological advantages of heat. Let me see if I can find this thing. Okay, here we go. A person in a sedentary activity loses heat at a rate of 400 BTUs per hour. Scientific investigation indicates the greatest bodily comfort is achieved when heat losses occur in approximately the following proportions: 190 BTUs by radiation, 120 BTUs by convection, and 90 BTUs by evaporation. All right. So again, you're going to be losing, you lose heat through, let's talk about convection. That's basically air currents moving across your body, taking BTUs away from your body. Okay. So you want to lose roughly by convection about 120 BTUs of your 400 by air moving across your body. All right. 90 BTUs is through evaporation. Well, that's sweating if you're at activity, but if you're just sitting there, that's breathing. All right. Every time you exhale, water vapor leaves your body, takes heat away with you. All right. If you're working out or doing something else, well, then the sweat thing is going to kick in, and that's going to cool you down by evaporation. But most of the time, if you're just sitting around doing nothing, eating Cheetos, it's going to be through basically breathing. The rest is radiation. Your body with clothes on has a surface temperature of about 70, what is it, about 78 degrees, 76 degrees, I think. I can't remember this. No, I'm sorry, 80, it was about 85 degrees. Your body with clothes on has a surface temperature of about 85 degrees. If the surfaces around you are much colder than your surface temperature, you're going to transfer heat from your body to those cold surfaces by radiation, all right? And you're going to actually feel chilly. If you're standing next to a cold window, boom, that window is going to suck the BTUs out your body, and you're going to feel cold. If you're standing next to a warmer surface, something that's been heated by radiant heat, the surface has been warmed up, you're going to control how your body loses heat. So that's kind of cool. It's just an interesting thing to read about. Okay, and we've used this thing for years. My dad handed it down to me many years ago, but it's fascinating reading, absolutely fascinating reading. All righty. Charlie, boy, you trained you in Wurzbo in a brick warehouse on the North Shore 25 years ago. Good Lord, that was a long time ago, wasn't it? All righty, terrific. Now, what else do we have here? Mr. Shoup, remember that bar in Plymouth Center, Matt? I don't want to know. Okay. What Mr. Shoup has been up to. All right. Excellent, folks. Keep those questions coming in. We'll stay on as long as you guys want. Okay. There's what did we have? 83 of you still left online. So, John, is Mr. Messenbrink still with us?
Nope. John had a roll about 3 minutes ago.
I think he was tired. John went camping. All right, over the weekend, and when you're a grown up and you go camping with kids, you just don't sleep. You forget about it. If it's a 3-day camping trip, it's 3 days of not sleeping. So when you get home, you need to rest from your little vacation. And if you reach a certain age, you don't have to go camping anymore. Just the way it is. All righty, excellent. Folks, keep those cards and letters coming in. Let me see if we have any more questions from the Peanut Gallery. This has been fun, kind of going back over radiant heat, I think here's a pop quiz for the guys who are still online. There's 79 of you. Here's a pop quiz. Let me ask you this. What's the most effective, now let's just say, what's the best way to install radiant heat? If someone asked you, what's the best way to install radiant heat? What's the best way to install radiant heat? Type in your answer. I'd be interested in what you have to say. And Rich Kester says me, Tossie, and my brother are hanging outside, drinking beers and smoking cigars and watching you guys on the big screen. All right, have the whole neighborhood come on in, man. That would be fantastic. Have the whole neighborhood come on in. I like it. What's the best way to install radiant heat without leaks, says Dan Cook. Properly, says Rich Kester. All right, very good. In a slab, electric. Woo, I like that one, electric. What else do we have? How is heat loss from in-wall convectors calculated? That's a question I'm going to have to think about there. Curtis says in concrete before the pour, above insulation, concrete slab. Depends on what you want to heat. Says Charlie on the slab. Okay, that's interesting. It's kind of a trick question, I guess. What's the best way, Dave? What's the best way to install radiant floor heating?
Make radiant fit the house. Don't change the house to fit the radiant.
Thank you. Make radiant fit the house. What's available to you? If you're doing a second floor bathroom, I don't care how much you love concrete slabs, that ain't happening, right? It's just not happening. If the house has already been framed and it was not framed to accept an 1.5 inch pour of lightweight concrete or whatever, well, that's off of the table. You might have to do a plywood and aluminum underlayment above the floor, or you might have to go in between the floor joists. To me, the best installation method is the one that makes the most sense for the application you're looking at today. Tomorrow's answer might be different. All right, tomorrow's solution might be different. As Dave said, design the radiant to fit the house. Don't do it the other way around. Okay. Yeah, we love putting tubing in a slab. Why? It's easy. You just tie it to the wire mesh or staple it to the foam insulation and let her rip. Okay.
I have all three in my house. I have slab, I have plates and I have suspended. So,
Mm-hmm. Yep.
and it was just the way the house was. I mean, my house was renovated, so I gutted it to the studs, and it was a slab on grade house. I actually chopped out the slab to put the radiant in. So, but I was already pulling out. I was already chopping up about 35-40% of the slab because I was rerunning waste lines and whatnot. So we just went the complete way, and instead of trying to save a little bit here and there, I just chopped out the entire slab. Contractor said, "All right, I'm looking at a half a day's work to go from 30% of the slab to 100% of the slab." So that's what we did.
Yeah. And for everybody out there listening, what Dave just said is very indicative of how he does everything. If me, I'm looking for shortcuts every single time. Dave says, "Nah, we're going this far. Let's finish it and do it right." Me, I'm saying, "No, we're doing this, and that's if I got to lift this stuff out, that's all I'm doing. Everybody else got to work around me." Dave, no, he'll go the extra mile, and then that's Dave does everything that way. Every whether you're presentations, training, the whole shooting match. That's Dave in a nutshell right there. Just so you know what I have to deal with. Okay, what do you mean by suspended? Suspended tube. Ooh, suspended tube. What do you mean by that, Dave?
Where the tubing is in an air pocket. So where a plate system is underneath the floor and you have the plates installed right to the subfloor, tubing snapped in, insulation shoved up tight. Suspended, you eliminate the plates, you take the tubing and bring it off the subfloor about an inch or so, and then insulation underneath that, creating a 2-inch air pocket. So when you go with a plated system, we're working with direct conduction, and you're getting that heat transfer right from the tubing into the metal plate, right into the subfloor. When we do suspended, we have to heat up an air pocket, which then heats up the floor. And when you choose one versus the other is going to depend upon the heat loss of the structure. So the areas and also the R value that we have above it. So in my house, where I have suspended is my bathrooms, limited outside walls, tile floor. The plated areas are where the carpet and hardwood areas are, the bedroom spaces, so taller ceilings, more windows, more heat loss to the space. I needed to have, it was a higher BTU per square foot. The reason why I did both on the same floor of the house is because I did one manifold and I can do one water temperature. So that manifold is located up in the closet up on the second floor and goes out to all the spaces. So now I have one, you put plates in, you drop your design water temperature between 25 and 40 degrees for the design temperature. When I took the plates out of those bathroom spaces, it raised the water temperature closer to what I had for the plated areas. So it was just an easier install. So Nick, he asks, which one is better? And it's not. It's not either one. It all depends on what you're trying to do. And it was an easier way to install the system rather than going to two temperatures, two separate manifolds that I would have to put upstairs in the house. So it was just an easier boiler room piping for me too, and making life easier.
There you go.
So I did follow your way, John.
Thank you. Thank you very much. I appreciate that. Throw me a bone here, buddy. A good way to look at this, and as really well explained, Dave, a way to look at this is if I had one room and I could choose plates or no plates, the advantage of plates, okay, the advantage of plates is lower water temperature. It's all conduction. I'd have a noticeably lower required water temperature to heat that room. If I took the plates out and suspended the tube, the output would still be the same. The BT load of the room would still be the same. The required surface temperature of the floor would still be the same. The only thing is I'd need a higher water temperature to get there. That's the only difference. Okay, so it's one of these things, it's never wrong to use plates in that it's never wrong to design around the lowest possible water temperatures, because one of the things designing around the lowest possible water temperatures will do for you is it gives you room to change stuff if something should happen. Like they said, oh yeah, we know you designed for this carpet and pad, but Last minute, we decided to go with this carpet and pad that's got a higher R value. So, oh crap, what am I going to do now? Well, if you designed around the lowest possible water temperature with plates, you've got some room to goose that. If you're going with a higher water temperature without plates, you might not have as much room, okay, to goose the water temperature. So that's a practical thing to think about. But if you know something, if it's a bathroom, nobody's going to carpet a bathroom behind your back, right? Not, well, never say never, but you know,
No.
it's probably going to stay tile. You're going to be fine there. Kitchen, same kind of thing. You know, entryway, you might be fine. So that's a ways to think about that. Cool. Excellent. Excellent. Is it because the convected heat of the suspended tubes needs to hit the floor to become radiant, i.e. higher temperature for suspended? I guess that's one way of looking at it. What you're
Less
doing
mass.
is
You got
yeah,
less
it's
mass.
less mass. Yeah, exactly right. The mass includes now an air pocket. All right. What you're trying to do is create a warm air pocket, and that pocket gets warm. It heats up the subfloor, which heats up the underlayment, which heats up the finished floor, which heats up the room. Okay. So you've got to create an air plenum or an air pocket underneath the floor. So your insulation becomes real critical here. If you just use plates and you put the insulation right up tight against the plates with no air pocket, okay, now it's all conduction. You just the aluminum is a wonderful heat transfer medium. Sucks the heat out of the tubing, spreads it over a larger area, and whoop-de-doo, we're good to go.
Right.
And notice he said suspended tube and not staple up. Like I said, they talk about staple up, which you use with rubber tube or something like that, where you actually staple the tubing so it's in constant contact with the subfloor. There's some issues there in terms of what we call striping or hot spots, where you'd actually feel, you map that out. Hey, there's a tube. There's another tube. There's another tube. You can feel it with your feet. Okay. It'll still heat the room. It'll still satisfy the thermostat, but it's not the comfort level that you're looking for.
Right. And staple up a lot of times it has been trademarked by the rubber tube manufacturers. And when they want to staple it, what they're doing is taking the tubing and kind of squishing it so it has more surface contact to the floor itself. You try to do that with PEX tubing, you basically get line contact. You take a round tube, you're not squishing PEX tubing, so you basically have a point of contact. So that's why you want to look at it. So one of the other questions that came in was water temperatures. I mean, it could vary, but I would say a plated system, if you're looking at the heavier plates, you're probably around 115, 120 degrees, whereas your suspended is going to be around 140. So that's your big differences that you see, up to 180.
Mm-hmm.
I mean, you can do a suspended floor with 180 degrees. A lot of people will freak out. Well, no way, can't do 180 to floors. It has nothing to do with the water temperature. It all has to deal with the surface temperature that you end up with. So if you need to do it with 180 degrees to get to your design surface temperature, then you do it with 180 degrees. It's not beneficial to the system itself, but you do want to try to use the lowest water temperature as possible itself.
Got a couple of questions about noise.
Also, what's that?
There's a couple of questions from George Conrad about noise with the aluminum plates versus suspended.
Oh, that's the other big thing too. Yes, the lower the temperature, the less expansion you get too, so therefore the less noise you'll get. So, and I still remember the math, John. It's 1.1 inch per 10-degree rise per 100 feet of pipe. Is how much it's going to expand. That's just that number that's just ingrained in my head. So the lower the temperature, the less expansion. You think about that for a second. 1.1 inch per 10-degree rise per 100 feet. Now let's imagine you're running a system at 170, and I'm only doing that to make the math easy. What's the temperature rise? Where's the temperature start at? Well, what's room temperature? 70 degrees. All right, so our rise is 100 degrees. If you have a 100-foot loop raising 100 degrees, you're going to grow almost this much.
Mm-hmm.
Right? It's 10-degree rises. All right, so you're going to grow over 10 inches long just in that 100-foot loop. So that's why you got to watch out for that. And when you lower that water temperature, now let's say we go down to 120 degrees. All right, that's half. That's half the expansion that you'll see out of that. And then with the plates, they're holding the pipe in, and depending upon the brand of the plates on how they grab it and things like that, there's going to be some expansion that still happens, but then it becomes minimized, and then we start looking at modulate the water temperature, go outdoor reset with your mixing valves, and lower the temperature even more, so it's not slamming it with 120. It's going to modulate it between, say, that 95 and 120. So
another question about plates with noise. One of the things about plates is you always got to be careful how you staple them up. If you've got or screw them to the subfloor, like I know at Worsbo we had those thin double plates, okay, where they're 14 inches wide and they had runs for 2 tubes, and you'd staple those up. The thing with those is you stapled them in the middle. You didn't staple the wings. You let the wings go free, so that's where the plate itself could expand. And that made a big difference when people went crazy with staples and stapled the whole thing tight to the floor, including the wings. The plate itself couldn't expand and it would start to make some noise. So that's one thing to be cognizant of there. And different manufacturers have different requirements for their plates. In addition, those heavy-duty extruded aluminum plates are 4 foot long with heavy-duty extruded aluminum. Those things had little to no expansion because they were so heavy and dense, but they had a monstrous output. And those things never had a noise problem with those.
Yeah.
Okay.
The expansion is going to happen on the loops on the ends,
Right.
and it's only going to grow about that much because everything else is kind of secured in there. So you're not going to see a lot of that. And then if you do need to account for that expansion, that's when we throw in an expansion loop to let it grow. So as it's feeding a long straight line, you do a loop before you make a turn or something like that. So then you work out where the noise is going to occur, if any. So you control it from that area. Yes.
If you give the tubing somewhere to expand, that's where it will expand. If you don't, then it's going to expand where it damn well wants to.
Right. Want to use the plastic Mickey Mouse ears as the sleeves going through the holes, so the PEX isn't rubbing on the wood. You got plastic on plastic, keeping it nice and straight. You don't need to use a laser to drill your holes in your joists, but get kind of close. And use those plastic guides, so this way it's not rubbing on the wood as you go through. I mean, if you wanted to use a laser and if you've got one already, then great, use it. So this way you don't see any of that, rubbing along the sides of the joist as you're going through.
Oh, and another thing we've seen going in between the floor joist in plates, where you're making that 180 degree turn at the end of the joist bay. All right, to go back the other direction. A lot of guys will put a clip or a plate or some sort of a staple on the end of that loop, so the loop doesn't move. No. Yeah, let the loop move. Let that be a place for expansion. Absolutely.
Yeah, because that's usually up against the wall. That's 10 to 12 inches away from the edge of the wall, and nobody ever walks there. That's where the furniture is. Yeah, you don't walk there. The only time you walk there is when you're using the wall to hold you up. And at that point, you're looking for someplace cool. Yeah,
that's right. Tossie wants to know, which do you prefer, radiant floor or radiant ceiling installations? Well, I prefer radiant floor because there's nothing like being in contact with a nice warm floor. But if I can't do a warm floor, I'll do a warm wall or I'll do a warm ceiling. So yeah, it's just my own personal preference. And someone asked earlier about radiant wall. Radiant wall is the same thing as a radiant ceiling, only it's vertical. Okay, it's the same basic idea. You're turning the wall into a radiator. All right. And one thing we learned, and the installation is almost identical, the output's virtually identical, but one thing we learned about radiant wall is you never want to install radiant wall up more than 4 feet from the floor. So you want to stay within floor level to up to 4 feet, no more than 4 feet, for one very simple reason. People like to hang pictures. And what do they hang pictures with? Tube finders, also known as nails, but generally known as tube finders. So you keep it at 4 feet or lower, you're very unlikely to hit it with a nail. All right, from when they're hanging pictures. A lot of good questions here. How do I calculate the temperatures for pocket space and for plates? How do you calculate water temperature for radiant? Every radiant manufacturer will have their own installation handbook, and they'll have tables or charts in there that you can actually look. When you look at the installation method, you look at the BTU per square foot requirement, and you look at the finished floor R value, and you just follow these lines to where they intersect, and you go down and it'll tell you what the water temperature should be. And every manufacturer has their own design manuals will be able to tell you that. And I think based on what we're talking about here, it might be worth talking about in a future program on just an example on how to do that. Do you have a couple of plate brand preferences? Not really. I don't. Do you, Dave? I mean, they're an aluminum heat emission plate's going to work very well. The extruded aluminum is going to work a little bit better.
Yep.
So I pick the brand of the. If I were going to do a radiant heating system, I would pick a brand and use all of their components. Because if I'm using Worsbo pipe and someone else's plates and someone else's manifold, who do I talk to if I have a problem? All right.
Yeah.
If the system doesn't work, I call the tubing people, and the tubing's the only thing I've used. They'll come in and say, well, the water's on the inside of the pipe. See ya. You know,
Yeah.
You didn't. This isn't our system. This is just our pipe. Our pipe's working just fine. You want to be able to have help. Okay. You want to be able to have help. So I think pick a brand and use everything in their offering for that job. You'll be much better served, both for your peace of mind and for your customer and for the performance of your customer. That to me, that's the best way to do it. I'm not into cherry picking components. I don't think that makes sense.
Yeah,
Right.
yeah, and especially if you're going to use somebody to help you with the design work, do the heat load, put the materials list together, all that other stuff. So, and yes, when the system doesn't work, blame it on the boiler.
Yeah.
Thanks, Dan.
Thank you, Dan. Yes, indeed. Yes, indeed. Keith O'Malley says, my personal house with suspended only, good to 17-degree outdoor temperature. The room temperature would drop. Installed plates with the same water temperature was good until 4 degrees. Well, sure. Plates are going to give you more output at the same water temperature. That's universal.
Amen.
Yeah.
Yep.
That's a perfect illustration of what we were talking about, Keith. Absolutely.
Yep.
Absolutely.
You added more mass to the house. So, definitely right. Yep.
Now, here's a good question. Water temperature for the floor when you have oak hardwood flooring above. Roger, don't worry about the water temperature. Worry about the required surface temperature. What surface temperature do I need to heat the room? All right. Typical oak flooring, what's the what do they have for a maximum surface temperature for most like nailed down hardwood floors? I remember it being about 80 degrees.
80, you could push it to about 82 and a half.
82 and a half.
82 and a half degrees. And that's if you
not,
had. Yeah,
that's not water temperature. That's not water temperature, Roger. That's floor surface temperature. The temperature of the water is whatever you need it to be to get the surface temperature that you need to deliver the BTUs required. That's where radiant heating gets so darned interesting. All right. It's not about water temperature, what water temperature is too hot for the floor. It's what floor temperature is too hot for the floor. All right, so oak floor, 82 and a half degree surface temperature.
And that's going to be your, that's going to be your, oh darn it, I forgot the name of the wood, the type of cut of the hardwood floor. You got two different cuts of hardwood floor. You're going to spend a little bit more.
Right. Yeah,
I'm running a blank on it. I installed it in my house. That's the way I did it too. So I didn't have
plain sawn, quarter sawn.
Quarter sawn, that's right. So you want to go quarter sawn, you can get to that 82 and a half. If you sent regular oak floors, 2 1/4, 2 3/4 strips, then you're going to be around 80, 81 degrees. Pine gets you to 80. Wide plank pine, you're getting to about 77 because it's all about how hard the floor is and how much moisture is actually in the floor itself, in the wood itself, and how much expansion and contraction. All floors, no matter what, are going to expand and contract. Mm-hmm. That's also one thing to remember when it comes to radiant heating. A lot of people, the radiant heat killed my floors. No, it's the moisture in the air, man. It's winter, low humidity. It's going to shrink. In the summer, it's going to expand. So radiant heat is not driving it. It can, if floors get put down before they're acclimated, can mess it up. And believe it or not, it happened in my house. So yeah, I had 2 different deliveries of hardwood floor. So the second floor, I did the quarter sawn all throughout, and it's beautiful to this day. Then when they delivered the wood to the second for the first floor, I got some cupping. So my contractor had to come back and resand the floors down. So because it was not acclimated properly and not brought down in humidity levels or moisture levels, and it cupped. And I said, and he came to me and he walked up to me and said, "Oh, it's got to be the radiant." I'm like, no. Yeah. It's not the radiant. I'm like, it's September and I have 90-degree water going into the floor. 90, so yeah, it wasn't the radiant floor, dude.
Well, think about it. What would make a floorboard cup? meaning it's going to have moisture at the bottom, and the cells at the bottom are going to have to expand, and that'll cause the board to cup, right? Well, what
I'm
causes,
sorry, I crown the other way.
oh,
Yeah.
crown is the other, but what causes it to cup is moisture. Where's the moisture coming from? If you're putting it on top of concrete, it's coming from concrete, right? You know, it's not, if you put a
Yeah.
piece of hardwood down that's got 10% or 8% moisture content, and the slab has not acclimated properly, and the slab's got 25% moisture content, I don't care if you got radiant in there or not, 25 is more than 8. All right,
Yeah.
25 is going to give off some to 8 to make everything simple, and that floor is going to cut. That floor is going to cup. It's got nothing
Yeah.
to do with the radiant heat at that point.
Yeah. And
But
my
they always
floors
blame the
were-
radiant, right, Keith? You're
My
absolutely right.
floors were dry. Yeah, my floors were dry at that point. So there was, you know, the concrete was already in for at least 5 months before we put the wood floor down on top of it too. So, yep. Oh yeah,
So
he
my
blamed the radiant. Oh yeah, and he wanted to get the manufacturer of the wood floors out here and everything like that. And I was just like, okay, you know, you can do that. Come on out, take a look at it, you know, and you can see one set of floors to the others. That's hard, and it's all radiant. So, yep, definitely.
Yep, and good wood installers are using moisture meters, and the key phrase there, Keith, is good, good ones. Yep.
Yep.
Just blame the boiler again. Why not, Dan? I got
Yep.
forced air in my house. I'm blaming the damn boiler.
Yeah. One of the other questions came in said, what if you put a floor sensor into the system?
Well, what do we want the floor sensor to do? What's that floor sensor going to do?
Are you asking me?
Yeah, I'm asking you. Yeah.
Oh, okay.
What do we
Me
want
personally, I'm not a fan of floor sensors because it adds a level of complication to the controls of the homeowners. But the floor sensor, you can, depending on which one you put in, you can make it do a minimum surface temperature of the floor and or a maximum of the surface temperature. So it could actually be a hindrance in some accident, and also use it as protection. So if you don't want to get the floors too hot and have anything run away, you put the floor sensor in and put in that max temperature that it's going to reach. The problem that you can achieve is the air temperature says, all right, well, I'm not going to be where you want me to be.
Right. Yeah, it's like you got a thermostat in the room, and little Timmy goes, "Oh, buttons," and he presses the buttons, so the set point in the room goes up to 95 degrees. Well, if you have a floor sensor with a high limit to protect the floor, it says, "Well, I don't care what the thermostat's asking for. The most you're going to get out of this floor is 82 degrees or whatever surface temperature. That's it. That can protect the floor and protect the room." The other side of that, which you mentioned as a minimum, now that's important in solar gain areas, okay? Solar gain, especially with a higher mass system in solar gain areas. Imagine what happens if you got an area with a lot of solar gain, right? And first thing in the morning, the sun comes up, it hits that thermostat. That room never calls for heat the entire day because of the solar gain, all right? Sun goes down, all of a sudden the thermostat's got to make again, and it's spent in the entire day not heating up. Now it may take hours for that floor to catch up and keep that area comfortable. You might wind up with it being too cold. If you use a floor sensor to serve as a minimum temperature, then it doesn't matter that the thermostat hasn't called. We're going to try to keep that floor at a minimum temperature, so if the sun does go down, we don't have as far to go up. So that's an instance where you might use it on the minimum setting as well. What do we have from Keith here? My floors put in August with the most humidity, no cupping, but does shrink a lot in the winter. That's the nature of wood. If the floor is put in December and put in too tight, I can come in the more humid weather, and they always want to blame the radiant, but in actuality, it's the nature of the wood and the way it's installed. Absolutely, yes, sir. It is. Yeah, it's. Yeah, I ask people, have you seen hardwood floors cup or bow or whatever, cup, shrink, whatever, in rooms that don't have radiant heat? Well, yeah, same thing. It's the same thing that's making that happen is going to make it happen with radiant heat. The heat's just it's moisture, right? What does heat do to moisture? Dave, what does heat do to moisture?
What does heat do to moisture? It makes it warm.
Yeah, or it dries it out. Okay, and they might just dry it out. That's where I was going with this. Work with me, Dave. Dries it out. So yeah.
So George, no, I'm not saying they're a waste of money. Yes, you agree that it adds complication. I've went to so many job sites in the early days and troubleshooting, and the homeowners hated the radiant because they didn't know how it worked. And it was the, well, do I change the air temperature? Do I change the floor temperature? And a lot of times I would just go in there and just disable the floor sensor. So this way they just control the air, because that's what they were used to. And for some people, it was hard to explain how the system worked. Some of them got it, some of them didn't. And, people would change the floor temperatures and they had too many expectations out of it. So you turn that off, make it work. Now, granted, in my own house, nobody touches the thermostats but me. So, I don't have any floor sensors in my place because the other thing that I did is I've modulated as much as I can. So if you modulate water temperature, modulate the boiler temperature, between the boiler load and the boiler doing reset and the mixing valves doing reset, and then modulating the circulators, floor sensors become moot at that point, because now you're just really sipping BTUs into the spaces themselves, and I don't really need them. So, that's where they add that complication to the systems and how to control them and what settings do you put them at too. Yes.
That's a pop quiz for the group. Again, we've been down to 57. 57 you guys still left. Awesome. This is terrific. Thank you, guys. But here's a pop question for the 57 still with us. What's the easiest way, the simplest, easiest, fastest way to increase the floor surface temperature of a radiant floor heating system? What's the easiest way to increase the floor surface temperature of a radiant system? Type in your answer. I'm just curious to see where we're at. Simplest and easiest way to increase the floor surface temperature of a radiant floor heating system.
So let's see here. So let me see here real bit. So Nick turned around and said, can you guys do a class on radiant? I'm going to add it to the list. We should do a radiant class.
Why not? We can.
Why not? We can. Yeah.
We've done more than our share in our lifetimes.
So I would say, yeah, I'm going to put that on the list of classes to do.
All right, we've got some answers here. Turn up the pump speed.
Yeah, but it was already on high,
the surface. Yeah, raise the water temperature. Yeah. Increase the supply water temperature. Add more pipe. All right. I'm talking about the easiest way to increase the floor surface temperature. The easiest way to increase the floor temperature. All right. Yep. Two guys got it. Gary Griffin got it and Benjamin Hicken got it. Turn up the thermostat. All right. Turn up the thermostat. Odd things happen when you turn up the thermostat. You turn up the thermostat, the room gets warmer. How about that? All right. How about that? Since a radiant floor gives off heat based solely on its floor surface temperature, all right, and we want to make the floor surface temperature warmer, how's about we turn up the thermostat? All right. Put in more tubing. Yeah, hold on. The house is finished. All right. And I'm sitting in there and I want the floor to be a little bit warmer. Let me go put in more pipe. All right. No, change the water temperature. The thermostat setting stays the same. I boost the water temperature. That's not going to change the surface temperature, because when the thermostat's happy, it doesn't matter what water temperature it is, flow's going to stop. And if flow stops, the floor's not getting any warmer. Okay. So all those other things don't really do anything. They don't really do anything. You don't have to increase the water temperature. You don't have to make the pump go faster. You simply crank up the thermostat, because none of those other things, if the thermostat's still set at, say, 70 degrees, floor surface is never going to get any warmer, because when the thermostat's happy, everything shuts off. That's why there's no substitute for zoning and no substitute for thermostats in radiant floor heating systems. That's why we have That's why we have radiant floor heating systems with a lot of zones. And when you get a lot of zones, that means you get a lot of micro zones. And when you got a lot of micro zones, now we put stress on the boiler, and we can have short cycling issues, which is why we look at things like buffer tanks and things like that. That's just that was an interesting exercise. I'm glad you guys played. All right. But yeah, turn up the thermostat. Simplest thing. Open the window is another example. Either or they change the heat loss characteristics of the room, right? We've changed the heat loss of the room, either by turning the thermostat up or opening the window. Same thing, only different. In either case, we'll change the floor surface temperature. There you go. All right. Dan Cook's got to run. Dan, thank you so much, as always, for being with us. We love having you, man. Be good. Thanks for being here. And again, guys, as we said, we'll stay on until you are done asking questions because it's Wednesday night and this is what we do. When I was in college, Tuesday night was tavern night. So it was like another Friday night. When you're in college, sometimes it seems every night's Friday night. But at American U, Tuesday night was tavern night. And the tavern would have beer specials. And the DJ, I worked at the radio station, so we would have the DJs there and we would play music. And a lot of girls would be there to dance. And that was another Friday night. It was like a bonus Friday night in the middle of the week. So Tuesday night was always tavern night. We loved that. So I don't know what brought that on. Oh, because Wednesday nights Takeo After Dark night. It's not really
That's
tavern
right.
night, but we can play a little music if you want, I suppose.
Yes, for me, Tuesday night was wing night. So any Long Islanders here, it was a restaurant. They had a couple of places called Big Barry's, 10-cent wings. So we would show up there and all right, just throw out 100 wings, and it's good old beers being pounded down, and oh yeah, it was good. Wednesday night was the only night we stayed in to do homework. Because Thursday was ladies' night,
Yep.
Friday, heck, it was Friday. Monday, hey, Monday Night Football. So, yeah, and we never got any work done.
Never got any work. Yeah. Tuesday night, if you had an early class, you really tried to avoid early classes on Wednesday. Now, I always had an early class on Thursdays. One semester, I had an early class on Thursday, but I also had the early morning shift on the radio station. So I would get up about 4 o'clock, go to work from 5 to 8 at the radio station and do a shift. And then at 8:30, I had a class, and it was one of my favorite classes too. It was on drugs and psychopharmacology because I wanted to know what I was getting into, right? I believe in getting as much information as possible. But I had this stretch where I would fall asleep in class, and the professor always caught me, and he was funny as heck about it. He goes, "Oh, look, he's sound asleep again," and I would always fall asleep in class. And then he finally found out that I was getting up at 4 o'clock in the morning to go to a radio show, and then going to his class, and he kind of understood, but he still didn't like me falling asleep. So, but did well in that class. Learned about Thorazine. I know not. Don't abuse Thorazine.
Okay, all right.
As it turned out, the only controlled substance after that class, the only controlled substance I really abused were Twinkies. I just that was the safest thing to abuse was Twinkies. George Conrad's asking you all the questions, Dave. He's not asking me. I wonder what that means. Thanks, George. Don't give me a complex or anything. But David, what are your thoughts of installing radiant floors done with polybutylene in those old farmers that used Corlon? I don't know what Corlon is, but polybutylene, you can't get it anymore, but there's a reason. But Dave, since he asked you, I'll just sit here and wait patiently.
Oh, okay. Well, I would say don't mess with it. For one, don't mess with that tubing and just be careful of it out there. But, a lot of that older pipe didn't have any oxygen barriers on there. So it could be corroding and killing a lot of the cast iron and steel components that you have in a system. So if that is the case, if you're finding that you're changing expansion tanks every 2 years and circulators are seizing up on you, then I would probably consider going ahead and putting in a flat plate heat exchanger to isolate the two of them. So, and then on the heating side, make sure you're using stainless steel or bronze components compared to steel. Get rid of all the steel and cast iron on the one side, and then go to the boiler side. So yeah, like we said, we don't find the poly B around any longer. But hey, it's just a different size pipe. If you need to make connections, make sure you get the right connections. There are some manufacturers that are making PEX to poly fittings. Sorry.
Butylene.
Yeah. So coupling's the word I was looking for.
There you go.
Yeah. So you can find those. So but hey, if the radiant's still working after all this time, I mean, poly B hasn't been around in 25 years now, and if it's still working, it's still working. Leave it alone. It's
it must have been 97, 98 when it was finally just eradicated from our world, and then all those guys that were making polybutylene, started making PEX tubing, back then. But yeah, that was probably 97, 98 when that went belly up. Yeah, just the way it is. Keith O'Malley, is it possible to speak with you about a 10,000 square foot house I'm doing? Would like advice on pump choice. Basement is in slab, main floor is quick track, all Uponor, ready for finish, 8 manifolds. Sure, absolutely. You can call myself or Dave. Dave, you want to type in your both of our phone numbers, and you can call whichever one you want. Probably if George would call Dave, no doubt, because I guess Dave's George's favorite. Well, I chop liver, I guess. I don't know. But yeah, please feel free to call either one of us. Happy to do it. Happy to do it. Okay. Warm floor systems, you still run into those old poly B. Yeah, here's the thing. Everybody said poly B was crap pipe, and it just fell apart. It was crap pipe, crap pipe, crap pipe. All of it fell apart. No, that's not what happened to poly B. That's not what happened to poly B. What happened to poly B is this. Poly B plumbing had issues, and it wasn't all poly B plumbing. It was poly B plumbing on the hot water side, and it wasn't all poly B plumbing on the hot water side. It was poly B plumbing on the hot water side where you had highly chlorinated water, and it wasn't all poly B on the hot water side with highly chlorinated water. It was poly B on the hot water side with highly chlorinated water, and these specific fittings, I forget what the material was, but it was a plastic fitting that would degrade on the hot water side with highly chlorinated water, all right? And those would start to degrade and shrink a little bit, and you have leaks. That's what led to the downfall of polybutylene. It wasn't that the pipe was garbage. It was these fittings had massive failures, acetyl something or other. I can't remember the exact name of it. So it's important to, we in our world in general, we tend to paint with wide brushes and we don't look at the details. And the devil's always in the details. So it's not surprising that there's a lot of old warm floor systems with the poly B pipe that are still working. If there's no ferrous components and you're circulating the same water over and over and over again, and it's warm water, not hot water, there's no reason why that stuff's not gonna last for years, right? There's no reason why it shouldn't. Okay, it's just making sure you understand what it is we're talking about. People go, poly B, oh, that stuff's garbage. No, it was the fittings, man. And it wasn't all the fittings, it was those fittings on hot water sides with highly chlorinated water. So there's always, you always got to look beyond the headline and read the story, you know.
And then even added on top of that was also even the ones that had the aluminum rings, not the copper rings too.
Oh gosh, yes, that's right.
The aluminum rings even softer. So yeah. So, yeah. You know, so, and yeah, oh, it all sucks.
Yep. That's
and we, you know, and you and I had to battle that all the time just to try to get radiant PEX to get going, because everybody
and PEX for plumbing, you know, PEX for plumbing.
Oh,
boy,
gotcha.
And here's the thing, you know, getting PEX for plumbing started. This is a little trip down our memory banks here, but memory started selling PEX for plumbing 95, 96, 97. And people, oh, well, that stuff fails. I use copper because copper's proven. I don't use this experimental crap. Copper's proven. And I ask a guy, well, have you ever fixed a pinhole leak in copper pipe? Oh, yeah, all the time. What is that? What do you mean? That's a product failure. No, that's not a product failure. Well, yes, it is. How many holes did that pipe have in it when you put it in, right? Just the one, the big one in the middle. Now there's two. That's one too many. All right. That pipe had one job, keep the water on the inside. There's a pinhole leak in it now. Now the water's on the outside of the pipe. That's a product failure. There's no other way around it. It's a failure of that product to do what it was supposed to do. It's a product failure. And guys will say, well, no, that's happening because the water is acidic. I don't care why. Why isn't the point? The point is that it has two holes in it instead of one. And guys would lose their minds. They said, no, this is proven. It's this stuff. Oh God.
Yeah.
It's just.
I remember designing radiant systems. We're gonna put 10,000 feet of pipe in somebody's house and bury it in the concrete. But as soon as I brought up PEX plumbing, they're like, nope, doing copper. Wait, what? You just took pipe and buried it to never be seen again. Right? And you feel comfortable with that, but for PEX, for plumbing, you're not using PEX.
Not putting it in the wall. No, not putting it in the wall. No
way. Yeah.
And you know, these things over time it goes away. I mean, I think one of the things we started to do was explain to people, well, what if we had invented PEX first, and everybody grew up using PEX, and that's how they did plumbing, and then all of a sudden someone came to you and said, hey, we got this new revolutionary product. It's called copper, and you're going to use copper for plumbing now. And say, wait a minute. What are you talking about? What's wrong with the PEX? I mean, oh, you don't want to use that. You want to put in this copper because it's rigid, it's straight. You can make 90-degree bends and it'll look nice. I said, oh, well, is it going to be less expensive? No. Per foot, it's probably going to be a lot more expensive. And chances are someone might steal it and sell it for scrap, and you might have to do it again. Oh, man. But I got to use all these fittings, right? I don't have to use as many fittings now. So I use fittings so they'll go that way and nice and straight and plumb and all that, which is important, right? He says, yeah, but is it going to be faster to do it this way? Well, no, it's probably going to take you 2 times, maybe 3 times as long. And guess what? To make the pipe, make the connections, you got to use fire. All right, you got to bring fire into the equation, into not into tight spaces in houses made of wood. All right. And try and put this thing together that way. And no, we're not going to give you the fittings for free. No, we're not going to give you the torch. We're not going to give you the torch kit, the solder. No, you got to buy all that. You got to pay for all that. And it's going to have a better warranty. No, it doesn't have any warranty. What do you want a warranty for? Come on, it's copper. If the roles had been reversed, no one would have ever used copper in the first place, right? No one would have ever used copper. All right. And you still carry the scars. I had them for years. All the burn marks on my arms for years and years after I left the business of getting hurt. So it's just, I'm sorry. It was just a rant, and I have plenty of them. Hey, George is throwing me a bone here. Thank you, George.
All right, I'm taking
I don't
some
think
time
make
off.
Dave jealous. Okay, but thank you, George. I appreciate that. Would you still need a heat exchanger if all of the components in the radiant floor poly B were non-ferrous? No, you wouldn't need a heat exchanger. If the entire system was non-ferrous, the whole shooting match was non-ferrous, well, no, we've eliminated ferrous components from the system. There's nothing to rust. So no, you would not need a flat plate heat exchanger. Very good. Okay, excellent. George is giving me another one. Have I ever installed radiant tubing under granite countertops in kitchens? I personally haven't, but I've seen it done many, many times. And it's cool because unless you have a warm granite countertop, you have a cold granite countertop. And sometimes people like warm granite countertops. Some people like cold granite countertops. People who don't put the butter in the refrigerator like cold granite countertops. That's fine, But yeah, I've seen people do that. Run a little bit underneath there and warm that granite countertop up. It's kind of nice. And tell you what, take that one step further, George. Go wild with the tubing in bathrooms, man. Wrap the tub with it, okay? Do the decking around the tub, into the walls of the shower. Just that whole wet and naked thing. It's better to be warm, wet, and naked than cold, wet, and naked every time. I've been both in my life, and I got to tell you, I prefer warm, wet, and naked. So absolutely go nuts with radiant tubing in the bathroom. Absolutely. All righty. Sean McGovern. Oh, you got it. You're gonna look at it. Never see that pump for trivia. All right. We'll see what we can do there. Candy makers, pie makers. My wife like cold granite. Okay, very good. Now that's sure. There's people like cold granite for whatever reasons. I can remember years and years ago, we got a complaint from a customer who we put radiant floor heating in the kitchen and it went under the cabinets. All right, it went under the cabinets. And in the old kitchen, there was a little draft there, and the guy used to keep his beer under the kitchen sink, and it kept his beer at just the right temperature for him. He loved that was the perfect temperature for his beer. But now with the new kitchen, not only did they seal it up, but there's tubing underneath there that now he had warm beer, and he hated the radiant system because of the warm beer. I said, put it in the fridge, dude. Put it in the fridge. You'd be fine, And we've heard stories of people who store their onions under the sink and now it was warm and then turned into a hot house and the onions grew or whatever. I don't know how that works, but it's always something. It's always something. I go back to, now that Dan Cook's not here, we just go back to blame the boiler. It's the boiler's fault. It's not Oh, Nick, you thought you were the only one to do that in the bathroom, meaning I hope you mean going crazy with the tubing in the bathroom. Yes. Yeah, you put it in the walls of the shower, everything, man. Put it, build a little homemade towel warmer, just run tubing behind where the towel. If it's a bathroom mirror, not a medicine cabinet, but a big mirror, run tubing behind the mirror, man. It won't fog up in the wintertime. So that's all kind of cool stuff.
No. Don't do that. No, because it only defogs the mirror in the winter.
Yeah, that's what I said. It won't fog up in the wintertime.
Right. So you use the PEX plumbing. As you feed the shower, you put a couple of loops in there as you get to the shower. Do it on the plumbing side.
The hot water pipe. You. Now I know why George likes you better. All right. Now I know why George likes you better. That's some thinking, man. That's
And
some thinking.
charge
And
for
an
that.
upcharge. There we go.
Fog-free mirrors.
There you
And it's
go.
interesting. People, they don't get this right away. This idea, you bring it up to them. It's not a big idea. So I was in Manhattan once for a Christmas party, and we were staying downtown in a hotel called the Wall Street Inn, and old little tiny hotel right crammed in the middle of Wall Street. And my wife and I are there taking a shower before the party that night, and tiny little bathroom, so it instantly fogs up everywhere. I come out of the shower and I see this square, literally, a little 1.5 by 1.5 square, completely clear. The whole wall was mirror. So they had electric radiant right behind that one little spot above the mirror. I come jumping out of the bathroom, turned to my wife, and I said, "Oh my God, you got to check this out." And I'm like, "Wait a minute, you were in the shower before me. You didn't see this and you didn't say anything about that?" And I'm like, "This is the coolest thing." And she goes, "Yeah, and?" So it's amazing how people really don't get it, but it was too funny to, when you experience it for the first time. That's just, a really cool thing, if you
Yep.
can do that. So, yep.
Yep. Now, electric radiant. Now, there's a thing that we haven't talked about, but as now that we don't work for Worsbo, haven't for me, it's been 12, 14 years. 2007, 13 years now. So
Mhm.
I see an electric radiant actually is kind of neat. Okay, it gives you the opportunity to install it in areas where maybe you never thought you could. And there's a lot of different step warm floor or others, whether it's low voltage with a converter or different types of electric radiant that you can install to give you even if you don't have hydronics to give you a warm floor where you might want it, bathrooms and things like that. So it's an idea that I think has tremendous merit.
Yeah, it does have limitations, as in, the BTU output that you can get.
Right.
You can get more out of a hydronic system, but if you're looking at the warm floor, that bathroom tile, or even warming up the mirror, yeah, definitely. Yep.
Absolutely. John Randall says, I live in San Diego and never dealt with radiant heat, only forced air. San Diego, Southern California, you'd be surprised how much radiant heat actually gets done out there. And it's not, you got virtually non-existent heating loads, but usually it's done for just floor warming, just to keep concrete slabs, everything slab on grade, just to keep slab warm. See people put it in pool decks and things. It's all those different options. I have this thing about YouTube videos. I'll spend time going through old YouTube videos of the old Johnny Carson show because I'm a huge Don Rickles fan. He was one of the funniest people ever, especially when he was on the Johnny Carson show and his byplay with Johnny Carson. Well, he was on. There was one clip, and I watched it once. I posted it on Facebook, but I can't remember. I can't find it again. He was on with I think it was Leo DeRocher, the baseball manager, and Johnny Carson. And Rickles had bought DeRocher's old house in California that had radiant heat. And he was going into great detail about how to find a leak in the radiant heat. He had to call up DeRocher and get the plan so they could find the leak. And they wound up using a stethoscope to try to find the leak. And his explanation of that was A, very, very accurate, but B, hysterically funny, as you'd expect from Rickles. But go on YouTube, if you can find that, Don Rickles radiant heat, it really, really a funny clip. But that's in Southern California. And again, there are a lot of opportunities there just to keep things. Hey, if you don't have a warm floor, you got a cold floor, right? If you're in a bathroom and you want a warm floor, man. So it doesn't matter whether you're in San Diego or San Francisco or in North Dakota. Warm floors are nice. Okay. Keith O'Malley's wife grew up in Levittown. Oh boy, that's the home of radiant heat, and was mad when
Long
I said.
Island or PA?
Yeah. Was it Long Island or PA, Keith? So I was installing radiant heat because her feet always itched because the floor temperature was so hot. Yeah, those were very rudimentary, very crude systems, and they got cruder as time went on. But boy, oh boy, yeah, once people got rid of them and they lined everything with baseboard, it was just a different kind of heat, Thermal imaging cameras, absolutely. They you don't have to use the stethoscope or the old cat. Throw the cat on the floor. The cat will find the hottest
warm
spot
spot.
on the floor and lie down, and that's where the leak is. Or you mop the floor, and the part that dries first, that's where the leak is. You get a lot of different things. Okay. George Conrad. Hey, George starting to like me better, Dave. All right. Huge fan of Johnny Carson, Johnny and Betty White. Awesome. I tell you, the Carson Rickles, just the way the banter between those two and Ed McMahon, hysterically funny. And just go there, and they're all on YouTube. Just type in Don Rickles and Johnny Carson. You'll find hours of these things that you can kill. You can kill a day watching these things. All right. All righty. Boy,
And did you know Slantfin? The reason why they set up shop here on Long Island was because of Levittown.
Really? Well,
Yeah.
sure. Great place to sell a lot of baseboard, right?
They set up shop out here on Long Island just so they knew where they were going to sell a ton of it to those Levitt homes that were failing. So they had already I think they started off in Manhattan when they brought out the manufacturing out to Long Island. It's that they picked Long Island to be close to Levittown.
Yeah. Yep. That's little tidbits of trivia from Dave that just enhance our lives. I love that. Very good.
There's stuff shoved between my ears. I don't know why it's still there. Yep.
I know. Hey, listen, the stuff that you remember versus the stuff I remember, the stuff you remember is useful. I remember Gilligan's first name. Never going to make me a freaking dime, but I know Gilligan's first name, So can't remember to take the garbage out on garbage day, but I did today, by the way. But no, I remember Gilligan's first name. It is a wonder. It is a wonder. All right. Hey, we're down to 47 of you. Again, we'll stay on for a little bit if you guys want. But yeah, Keith, yeah, we're loving sharing this stuff with you. I mean, this is just, like I said, this is stuff that we picked up over the years, none of us invented this stuff. We just learned it, like anybody else. And just, we love the opportunity to pass it along. You don't, if you learn it and don't pass it on, you're kind of shortchanging everybody, I think. So just share. I mean, it's not like we don't own this info. We just collect it, and pass it on. That's all we do. Never, like Dan Hollahan once said, I've never had an original thought in my life. Just, if you steal from one person, it's plagiarism. But if you steal from a bunch of people, it's research. And I'm a good researcher.
I know. I got so much stuff shoved between my ears. Sometimes I don't know where I learned it from any longer.
Yeah. Well,
but it's a small industry, we sit there and think about this hydronics world. It's still a small industry, man, but it's a lot of fun. A lot of fun.
It's a lot of fun because it's something not everybody knows and not everybody's into. So it's kind of cool. All righty. Hey, folks, thanks again. 2 hours, 2.5 hours, 2.5 hours.
Yeah.
On a Wednesday night in June. What a great time to be alive, man. What a great time to spend with you folks. Thank you so much for the gift of your time. Really, really appreciate it. And, thanks for spending this Tuesday night with us. We can't wait to see you next week for episode 2 of Takeo After Dark, the summer school sessions. I like that title. We need a movie kind of trailer. That should be, we should have Ken Watson make us a trailer,
Oh yeah, we should give him more work to do right now. Yes.
I think so. It's why not, Oh, we had to have one last question come in. On a snow melt system for a pool deck, what would you suggest? I'm thinking about 2 sensors in the middle of the slab and maybe idle the slab. Depends on what you want it to do, Chris. Do you want the snow to never, ever, ever accumulate? It being a pool deck. Are you going to use, is it like a hot tub? Is the pool going to be used in the wintertime? Or you just want to, if you want to make sure it never ever accumulates, or do you just want to be able to melt it once it does? There's two different approaches. So it's going to depend on what you want. If you never ever want it to accumulate, meaning, the snow vaporizes before it even hits the ground, well then, yeah, you're going to want some sort of a sensor that's going to set a temperature and keep it at that temperature almost all the time. Be sure you have money to burn to make that happen. If you just want to melt snow that once it accumulates, then you have other issues. So you're year round and you're worried about ice. Okay. If you're worried about ice,
would be an ice prevention system, which is a little bit different than a snow melt system. So that's kind of like doing car washes in the winter. So you don't need to maintain a high temperature to, if you get a little bit of accumulation on that area, but it's eventually going to melt, you don't have to go so hot in order to do the phase change. That's the big thing is changing a solid water to liquid water. So if you're just doing a maintaining of the system, I don't know if you need two sensors. One's going to be fine unless you're looking at a solar gain on one spot and not on the other. Then you got to think about where you're going to put the sensor. So you just really need to look at probably maintaining 32 degrees, maybe 33. Idling when you put the controller into a system, if you've got a specific snow melt control, idling is usually around 27, 28 degrees. And then those also have moisture sensors that then turn on and crank it up to say 36 to 38 degrees, because then it says, all right, well, the slab is cold and I have moisture. That means it's snow. Let's send some BTUs out there. So that's what you're looking at. Have a hot tub and pool around 3,000 square feet of slab. Wow. Not a 3,000 square foot pool, 3,000 square foot of slab. So you might want to look into that combination controller. So where it's looking at moisture sensor and slab sensor, and you can, at least when you have that, you've got flexibility and expectations of the homeowners. You go ahead and put it on just maintaining slab temperature, and they come back to you and say, well, I had a $5,000 fuel bill last month. That's way too much. But that's the only control I got in there, and I don't want to have to chop up the slab in order to put a different sensor in there. So if you go with the moisture sensor, with the temperature sensor, and the proper controller, you're going to get a lot more flexibility out of the system itself. So
there you go. What brands? I mean, Tekmar we know is a leader in these kind of controls. Who else makes controls along these lines, Dave, that you're aware of?
Uponor's got their own right now. Tekmar's got one, and Heat Timer, I believe, has some snow melt controls also. What was it? Yeah, I think Heat Timer, and there was another one that I messed around with years ago, and I'm not sure if they're around. Maybe ETI was another sensor control company out there too. So take a look into those.
Okay, very good. Yeah. Okay. Yeah, Philip, I can take a screenshot of that and send it to you.
I already got it, John.
Oh, you got that? You're taking care
Yep.
of? Good man. All right. Very good. Very good. Very good. All righty. I think we're good here. I think we've got everybody. So great. Hey, folks, thank you so much. Appreciate the time, and we'll see you next week.
Yes, sir.
Part 2. All right.
Enjoy, y'all.
Cool. And say what again? Go ahead. I dare you. I double dare you. Say what again? All right. We'll see y'all later. Take care.
See you guys. Enjoy.